Brilliant. Yeah.
Call out the solution so we can write it down.
Okay. Then the two numbers on the right.
So now these are estimated as 3,500 nanometer at its brightest at 30 and 60 time. It reinforces as an order that we can cancel. Find theta at A reinforcement and B cancellation.
Two numbers on down. Then there's remember how we do crystallography. Do you remember how we do crystallography? Okay. Yeah, approximately. You will just do and whatever else to and we let it go to this extent. Then that part where you need part length. Scientists are supposed to R1 as well to value. Just scientists are supposed to R1 minus R2 over A. A is the size of the slit in between.
And 2.
Yes.
What's R1?
What's that?
R1 and R2.
Those are each of the parts. Each part there. You know that radiations will strike there twice, one at different layers. The difference between both the incident and the deflected for each is the R1 and the R2. So you can't get that value numerically. That value there is just plus minus 1 over 2. And so what are you doing now? And so what value has it given you? What value has it given you? So, anyway, So where are you at on it? Where are you at on it?
It says for scientific that I should use plus minus 1 over 2.
Mm-hmm.
Then,
For R1 minus R2, you use 1 over 2 as the difference. That's part difference.
that's D.
D is the size of that seed.
Yeah.
Yes.
Okay.
So which other thing are you using?
We have lambda. There's no N.
What do you want to get? N is 2.
N is 2.
Because there are two parallel radiations there.
The cost is 8 degrees.
Anyway,
The angle of transmission for reinforcement, the cost is 8 degrees.
still living.
Mm.
Okay. What does the English mean?
For angle of translation.
Yeah. Have you done that? Have you got it? I didn't.
22.9.
Still opposing each other. Mhm. Um, a parallel RC circuit is connected to the rainbows of frequency source. A parallel RLC circuit is connected to the variable frequency source. At 40 Hz, the total number of current is 2.8 A. At 70 Hz, the total current is 1.5 A. identified that the total variance is 2.3. Determine A, the resonance frequency, B, the quality factor, C, the bandwidth, B, the quality factor. You have to solve for that. Let's see the bandwidth. What's going to do? Yeah. If you can just still take the put on your right in front. At 40 hertz, total current is that. At 70 hertz, that is present. Mm-hmm. Mm-hmm. So the minimum frequency hertz is 70. Bandwidth is minimum frequency of hertz. Minimum frequency rather than bandwidth is supposed to be charge or quality factor. Yes, we just call it quality factor. Hmm? The bandwidth is supposed to be F2.0. Upper frequency half frequency and lower half frequency. Hold on. Okay. 2.3. Yeah. That is good. This is it. Yes, minus 5% plus 4.4. It's going 20. No, that's it now. Now we start from the lower. Bandwidth. Volunteer. 55. Okay, like the bandwidth. Yes, I don't know what's the QF? QF. QF, okay. Random QF. Last one. I do it. Oh. What do you get? Oh no, the answer. Who's it? Oh, which one? Do it. Yes. Where? Hmm? It will soon be time for break. Why? Do you have break? At all? Well, well, a series sections. A series sections consists of R equals to plus 5 ohms, N equals to 0.2 ohms, N equals 0.20 ohms. Yes. N equals 0.20 each. Then C equals 30 microfarad. The circuit current is 3.5 when connected to a 240 supply. A. All possible operating frequencies. Determine all possible operating frequencies. B. Phase angle. B. Phase angle. What is it? Resonance? No. What's this ones? to get that result to this. The first thing they ask you for now, all possible operating frequencies. Those are dependents, reactants. Those are the possible frequencies. Phase angle. No. Just get them normal. Get them normal. You get them. You know, when you get them as X, that's when you got them as free. That's when you got them as resistance. If you get them as normal parameter, that's when you are putting them as frequencies. Don't get XL is not equal to 2 pi F, which is angular minus 2 N. That's one I have frequency. Get all of them as their reactants. You know what I'm saying? The value of the frequency in each of them is to be the same. The value of the frequency in XL is the same frequency in XC. So what you're supposed to get is just to get XL and XC. That was. That was. So like I said, you get resistance. To get the possible frequencies. Z is equals to Z is equals to V over A. V over A. Z is equal to V over A. Over I. V got now. That is impedance. And substitute the values xl minus x squared equals to 68 and 57 squared and 55 squared. Open bracket xl minus xc close bracket squared equals to open bracket 68.57 close XL, open bracket, XL, minus XC, close bracket, square, equals to, open bracket, 68.57, close bracket, square, minus 45 squared. Yes. 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 Why did you like Sandra? Right. Okay, so for in series, generally ask the question. So, generally, the question was okay. So it's not. Okay. Capacitive sections. X known as XC was minus 51.7. Is it minus 51.74? Let me call gently. Hold on. This is something that is supposed to be very simple and straightforward.
So now the first is eight. But
Okay, so which one is it?
I found resonance, point by resonance, eight.
Okay. So how about which one is the meaning?
Frequency at half of the maximum point.
Yeah. What is it?
Frequency at half of the maximum point.
You don't know what it is? Frequency at half of maximum current. You open up. Just try first. I'm really not. Okay. Just try. Try maybe. First one, so try maybe 2. So, let's just check online to see it. Just check online to see how to solve it. Check online and check inside the split. Okay. Okay. What aspect now? Which aspect? Frequency what? What's the issue? And resonance. So let me see what it is. This is come out there. This is come out there. Why do you do this? Yes, let's go to. Let's go to waves. So waves. So, different ways. We're going to sound wave. The sound wave of frequency 500 Hz travels through air at 343. Travels through air at 343 meters per second. Determine the wavelength and the period. So 343 meters per second. Yes. When? 0 point. Okay. So what next? The visual emits a sound of wavelength 0.80. The visual emits a sound of wavelength 0.80 meter. The speed of sound is 320. The speed of sound is 320 meters. Have you got it? For which one? We know the period. Yes. The sound wave has a period of 4 meters per second, examining the frequency and the wavelength in air. The sound wave has a period of 4 ns. The sound wave has a period of 4 ns. Yes. Determine frequency. Determine frequency and wavelength in air. Determine a speed. What is it? Frequency and wavelength in AAC. Then frequency 250 wavelength. What's wavelength? How do you get wavelength? A sound wave travels 2.5 kilometers in 7.2 seconds. Determine A. Speed. B. Time required to travel 1 kilometer. In 7.2 seconds. Determine speed, time required to travel 1 kilometer. The sonar pulse travels through space water at 1.5 meter per second. The echo returns after 3 seconds. Determine distance of the seabed. A bat emits ultrasound of frequency. A bat releases ultrasound of frequency 45 kilohertz. Frequency 45 kilohertz. The echo returns after 0.18 seconds. The echo returns after 0.18 seconds. The speed of sound is 340 meters per second. The speed of sound is 340 meters per second. Determine distance to the obstacle is right. Wavelength of the ultrasound. Yes. Oh, yeah. It's only for. It's only for. It's only for frequency 256 hertz. Producing sound in air. Should I just put the solid on the volume and not something? Yes. No? A loudspeaker emits 800 decisions in 2.5 seconds. Determine frequency, wavelength in air. Agree. The wavelength of sound wave, wavelength of the sound wave is 800 oscillation in 2.5 seconds. Frequency, wavelength in air. But this one is the wavelength of the sound wave in steel is 8.5. The speed of sound in steel is 5,200. I wish you can understand me. Just be active, be responding. Yes. Sound wave travels through the three medias, air, water, and steel. Its frequency is 1200. Determine the wavelength in each media. The sound wave enters water from air. Frequency goes to 1,500 Hz. Determine the wavelength in air, wavelength of water, which quantity remains constant. The sound wave has frequency 720. And echo is length 4.8 seconds. Start shouting. Speed of sound equals 340 meters per second. Determine distance from the reflecting cliff, time required for the sound to return from a point twice as far away, The sound has frequency equal to 2.5 hertz, amplitude 3 millimeter, amplitude 3 millimeter, speed 345 meters per second. Determine wavelength period, number of complete wave occupying a 20-meter corridor. My next two sound waves has frequency 520 hertz and 528 hertz. Determine A, bit frequency, B, number of bits heard in 15 seconds. Question 18. Question 18. A sound source emits 1.2 times 10 to the power of 6 oscillations. Frequency is equal to 600 hertz. Determine total time of session, length of the wave train in air. Question number 19. An aircraft emits a sound the pulse reflects from a mountain. This pulse reflects from a mountain and returns after 5.8 seconds. The speed of sound decreases from 340 meters per second to 330 meters per second. Because of temperature changes halfway through the journey. Because of temperature changes halfway through the journey. Reasons. A sonar transmitter emits pulse at a frequency of 80 kilohertz into seawater. Where the speed of sound is 1,500 meters per second. There. A submerged object is detected. A submerged object is detected 3.60 seconds. The distance to the object, determine the distance to the object. The wavelength of the transmitted sound. Yeah. The distance. The two sound wave have frequencies 520 hertz and 528 hertz. Determine a bit frequency. Determine bit frequency, the number of bits heard in 15 seconds. Okay. An aircraft emits a sound pulse. An aircraft emits a sound pulse. The pulse reflects from a mountain and returns after 5.8 seconds. The speed of sound decreases from the speed of sound decreases from 340 meters per second. To 3,000 meters per second. Yes. Are we on a break now? Yes. Okay. So good everyone. And we're going to be going into a new aspect. And we're going to do radioactivity. We're going to do radioactivity. Yeah. All right, so we are looking at radioactivity. So we are on radioactivity. Physics. So this is much. So we will begin. Radioactivity is just the spontaneous degeneration, disintegration of a nucleus. Radioactivity is the spontaneous disintegration of a nucleus. Expression of the plus. And the reactions that undergo around this process is referred to as nuclear reactions. It's referred to as nuclear reactions. So when we hear the word nuclear reaction, what does it mean? We're talking about some set of reactions that affect the nucleus, cause disintegration of the nucleus, and eventually lead to the release of particles such as protons, neutrons, electrons. These radiations released will be studying their properties and also energy. And also will be solving questions, likely questions that are coming out in the course. Okay. So Nuclear structure. Another process is small dense nucleus and the center surrounded by electrons with discrete energy level. Structure of an atom. The nucleus, electron, very small things. The nucleus are small, dense, and positively charged. That's very different. Proton and electron. Electrons are negatively charged particles moving around the shells all the time. Most of the proton is sent to space. Electrons, nucleus, this is the nucleus there. And you can see different orbits orbiting around here. The electrons revolving around. So, nuclear structure is still a nuclear structure. Protons and electrons are building blocks of the nucleus. They are collectively called nucleon. They are collectively called nucleon. As you get it. Protons and electrons are building blocks of the nucleus. They are collectively called nucleon. Comparison of proton and neutron. So we have properties like properties like charge, relative mass, location, who discovered those particles, as well as the role in the atom. So protons have one positive charged particle, relative mass of 1 and unit mass units. Neutron number 1 unit slightly heavier, and both have nearly the same mass. Location. They are found located within nucleus, join the nucleus as well. And keep my protons in the identity of the element. Now, discovered by E. Goldstein, Chadwick. So Goldstein discovered the proton, Chadwick discovered the neutron. Rule in atom. What are the rules in atom? Designers atomic number. Design atomic number contributes to mass number and stability. So neutrons affect the mass and stability of the nucleus. So interaction in the nucleus. Electrostatic force. Protons repel each other due to the positive charge. Strong nuclear force, a very strong attractive force, and unconscious proportion holds the nucleus together. The nucleus symbols of rotation. We have nucleus symbols. The nucleus represents this. The number up is the atomic number, atomic mass, and 1 down is your atomic number. Example, hydrogen and the proton, and the helium and carbon 14 and 56. So, all of those things together form the nuclear structures. So isotopes, isobands, and isotopes. So the isotopes, same Z number, atomic number. Isotopes have same A numbers and different Z numbers. They have the same mass number and different atomic number, different protons, different elements. Isotopes, same N, different Z, have the same number of neutrons, different atomic numbers. They are different elements. Examples of isotope of hydrogen have protium, deuterium, and tritium. Example of isotopes the 14. We have them as well. So isotones, same N equals to 8, different Z equals to 6, 7, and 8. So summary of table, type, same, different isotope, isotope, and isotopes. So Z, protons, A, mass number, and N, neutrons. Summary of table, difference, neutrons, A, mass number, protons, and N, neutrons. Then you have the protons and A, mass numbers. These are examples. Okay? Empirical formula. R equals to ROA is power 1/3, where R is equal to the nuclear radius. Are we together? And what else is equals to this number? RO is equals to 1.3. Equals to 1.3. So, yes, empirical formula R equals to RO is power of 1/3. Then you have where R is number nuclear radius, A is mass number, RO is 1.2 times 10 to the power minus 15 m, which is a constant. Key point. Nuclear radius is proportional to A, not A. Doubling the mass number. Doubling the mass number increases radius value to 1/3. 1/3 is 1.26 times. The nucleus is about 100,000 times smaller than an atom. And here's what the nucleus looks like. Significance helps in understanding nuclear size, collision, cross-section, and in calculations involving nuclear volume and linearity. Okay? Okay? Next slide. Nuclear density is approximately constant for all nuclei, regardless of their size. Formula. Mu is equals to AMN over 4 pi r cube. Key points. Key points. Nuclear management. So the mass, binding energy required to the nucleus, the amount of energy required to separate the nucleus. Mass effect is the difference between the sum of the masses of the individual neutron and the actual masses formula, change in M is equal to Z plus NM minus N over bracket A comma Z, where AM, that's change in M is equal to mass defect. Z comma N is equal to number of protons and neutrons, NYN as mass of proton and neutron. Mass AZ fractions of nucleus. Change in N is always positive, which represents the missing mass converted into binding energy, and is related to binding energy by EB is equal to change in MC squared. Okay? Example, for helium atom, Z is equal to 2, N is equal to 2. ZNP plus NNN is equal to 2 multiplied by this plus 2 open bracket plus 2 open bracket 1.0086 4.031882. So we have so if Z equals to 2, we also have where it is equal to ZN plus NN equals to 2 open brackets 1.00722 plus this is equal to this. That's that point. Change in is equal to 4.031882 minus 4.001506. This is equal to 0.0303. So that is systemic mass units. EB equals to this, which is equal to this, and this. This is the mass mega electron volts per atomic mass units. And it is measured in mega electron volts. Significance, mass effect is the origin of nuclear energy and stability. Next, Fourier fraction. Fourier fraction is the fraction of nuclear volume actually occupied by a nucleon. Formula F is equal to volume of nucleon over volume of nucleus, where volume is equals to what? Volume of nucleon is equals to 8 and 4 over 3 pi r 3. So, Rn, then 1 minus 2 plus 10 minus 5, 10. Volume of nucleus is equal to 4 pi, 4 over 5, 4 over 3 pi r. Then I have this equation. Simplify F equals to this, have F equals to 80%. Key point, only about 50% of the number volume is occupied by volume. The rest is empty space where nuclear photons. This explains why nuclear are mostly empty space. Take away, nuclear are mostly highly compact or mostly empty spaces with strong nuclear forces. Okay? Discovery of radioactivity. Prior discovery. The discovery of radioactivity was accidental and opened the door to a new era in physics. The experiment in 1896. The experiment in 1896. In 1896, Baker was studying fluorescent material. He wrapped a uranium salt in black paper and placed it on a photographic plate. He exposed the plate to sunlight to see if the uranium fluorescence could affect the plate. On cloudy days, he left the setup by a window when it developed the plate. It was exposed even without sunlight. Uranium salt K2U over. Then you have its conclusion. Uranium emits a type of rays that can pass through paper and expose a photographic plate without any external presentation, which is the next significance. First evidence that some elements emit spontaneous radiations mark the beginning of the study of nuclear physics, show that the atom is not invisible. Inspired further research by Curies and others. So these are the person took steps in studying radioactivity. Maria Curie, they extended the world of work of Henry Becquerel and made groundbreaking results that shaped the field of radioactivity. Methods and achievements. Developed technique to measure radioactivity. Using ionization of air in an electroscope. We set several ions on pitch lead or to extract minute amounts of radium. Establish radioactivity in an atom property, not the chemical. Nobel recognition. 1903 Nobel Prize in Physics. Shared with Becquerel, 1911 Nobel Prize in Chemistry. Awarded to Maria Curie. Significance: the Curie's work laid the foundation for modern nuclear science and the discovery of many radioactive elements. Natural radioactivity is the spontaneous emission of radiation from unstable nuclei present in nature. Characteristics: occurs without any external influence. Some elements are unstable nuclei and any radiation will become stable. The radiation emits can be alpha, beta, or gamma rays. The process is random and independent of physical or chemical stability. Naturally radioactive elements. Symbol type of radiation. We have radium, symbol U, type of radiation, alpha, beta, and gamma. Thorium, CH, alpha, beta, and gamma. Radium, SAM, alpha, beta, and gamma. Polonium, symbol is PO, and type of radiation is this. Actinium, elements, AC, alpha, beta. Importance: basis for geological dating technique, uranium leads. Importance in the therapy, diagnostic research, source of nuclear energy. So, artificial radioactivity is a phenomenon in which stable nuclei are made reactive when combined with energy pattern. Without experience. So this is like alpha particles and combined through the foil towards the nucleus. Key points is covered by an extracellular fold, achieved by combined stable nucleus of alpha particle. Helium nuclei. The target nucleus became unstable and emitted radioactive particles. This was the first laboratory to induce nuclear reaction. Okay, then, this was the first of them. Example of artificial radioactivity. Produce nucleus, type of radiation emitted. We have this, we have this. Okay? So, okay. Use a smoke detection, AM, cancer treatment, targeted alpha therapy, industrial sickness gauges, space, jazz, silent P. 236. Beta radiation consists of high-speed electrons or positrons entered from the nucleus during reaction. Two forms of beta radiations. We have the beta minus and the beta plus. Beta minus is the emission of an electron, E minus, and beta plus is the emission of a positron, E plus. Occurs when a neutron in the nucleus changes into a proton, emitting an electron, and an anti-neutrino. Occurs when a proton changes into a neutron, emitting a positron and a neutrino. Nuclear equations, N is equals to, N gives you P plus E minus plus VE. Then P gives this. So we have two nuclear equations. Okay. Penetrating powers. Moderate penetrating power stopped by a few millimeter of aluminum, 18 of sheet of plastic. Then we have properties: charge, beta and beta plus, mass 1 all over this. Then we also have speed up to 0.99. Then we have higher electricity power than alpha radiations. Then deflected by electric and magnetic, beta towards plus plate, beta towards the plate. Then we also have uses: thickness, gauges, medical tracers, e.g. Indomie. I did 131. We have contrast. Then we use beta therapies. Then we utilize beta therapies. Then we utilize beta therapies. Research in nuclear physics. We have beta plus emission of positron. Emission of the positron occurs when the proton changes into a neutron, emitting the positron and a neutron. So you have P to give you neutron plus electron. What is it? That's proton. Well, anyway, it's CP. No, that's electron. Anyway, CN. Anyway, it's P, proton. N is neutron. E is electron. And VE is frequency. You get that? So, penetrating power, moderate penetrating power is covered by a few millimeters per minute. Then, we take a sheet of plastic. So that is it. Type of radiation, gamma radiation. Gamma radiation consists of high energy electromagnetic waves emitted from an excited nucleus. So we look at them in terms of their nature. And so nature have gamma rays are photons. Gamma rays are photons. And they contain packets of energy, no mass, no charge, no less mass. Symbol is gamma. Carbon dioxide of light is equal to 3 power of 8. That's anytime when I said loses excess energy. Yep. Oh. Yes. Any radiation has the ability to emit light. Put the mic up. So we have emission decay equation. In nucleus, X is an excited state. And the gamma photon responds to a lower energy state. We have this equation, then we have this penetrating powers. Penetrating power. Penetrating power, very high penetrating power requires thick layer of concrete to absorb. You have paper, you have aluminum, you have lead, concrete. Uses cancer radiotherapy, sterilization of medical equipment, industrial radiography. You have food irritation and purification, tracers, and nuclear medicine. Those are the next slide. So we have types of radiation, properties of nuclear radiation, alpha particle, Thank you so much. Properties of nuclear radiation, alpha particle radiations, define their physical nature, analyze their abilities, penetration, inflicting power, and behavior effects. Analyzing powers. The ability to produce atoms in matter, they have alpha rays, beta rays, and gamma rays. They have speed, alpha rays, they have beta rays, gamma rays, and that summary of properties. And when we are summarizing properties, we are looking at this three only. We have nature, helium plus proton opposition, electromagnetic radiation, charge plus 2 plus ED over plus E plus B plus. And we have 0. Gamma is literally inert to many of the reaction processes. It's inert to many of the reaction processes. So speed, we have -1 to 2 extended to a y, the data set of course 0.996. Again, we have C to give you 3.0 raised to the power of 8 meters per second. Represent our charge. So mass for you. And for electrons, which are better because they are extremely smaller compared to others. We have this in as well. So, in terms of speed, deflection in the magnetic and electric field, slight due to my mass for our fan, but it deflects D and B plus. When it comes to gamma, no deflection. When it comes to gamma, no deflection. Then you also have what? Behavior in electric and magnetic field. Slightly deflected. D rays toward plates, gamma rays, no deflection, beta plus rays towards plates. Also, we have effect on living tissues. All human at high doses, damage decreases in order this. So that's that for that. Next slide. And the next slide. And the next slide. So we have key points about this. Each unstable nucleus has a certain probability of decay per unit time. The probability is independent of the age and the history of the nucleus. Here you have an example of a nucleus radioactivity due to emission of radiation. There will usually be a change in the size. So the probability is independent of the age and the history of the nucleus. The number of undecayed nuclei increases with time. So the derivation of the decay law, let n be the number of undecayed nucleus at a given time. During a small time interval, the T from the nuclei decay rate of decay, number of under decaying nuclei. So Dn change, and the change in distribution number. In time, we give this. I think this equation is a bit familiar to our lessons. Okay? Let's play. Decay constant, gamma. Decay constant is the probability of decay unit time for a single unit nucleus. Key points. The characteristic constant of a radioactive nuclide, independent of temperature, pressure, chemical state, and external conditions. So, it determines how fast the substance decay. SI unit, larger value in gamma decay means faster decay. Definition: probability of decay of the nucleus per unit time. It can also be defined as gamma equals to -1/n, then rate of change of n. So, for example, if n is equal to this, then the probability that a single nucleus decay in 1 second is that. Okay? So, half-life, T half. The half-life is the time required for the number of conjugate nuclei to reduce to half of its initial value. So, key points: after one half-life, n is equal to n0/2. The derivation from decay law, n is equal to this. After two half-life, n is equal to n0/4. And t equals to t half, n is equal to n0/2. After n half-lives, n is equal to n0/2. It's about n0/2. Then we have this, and we have this. Half-life is specific to each radioactive nuclide. Then you have this. Then n versus t. You can see that there is an exponential decrease in this. For example, carbon 14. This is the formula. We have this reality now, gives the half-life, and this gives the decay constant. Yes. It's a constant from certain materials. Different materials have like an half-life. Okay. Some materials disintegrate faster and they lose out of their mass faster than some other materials. Okay. So the mean life is the average time a nucleus exists before it decays. Key point: it is the reciprocal of decay constant, the average life of a large number of decaying nuclei. It's longer than that. Next second. Next. Derivation. Mean life is the average time before decay. T is equal to this. Is equal to 1/. T is equal to 1/. This. Example: T equals to 10 days, and it's equal to 1.44. This 10, which is equal to 14.4 days. Significance: mean life is useful in nuclear physics calculations, reactor kinetics, and understanding the average behavior of unstoppable nuclei. Okay. Activity of a radioactive source. Activity is the number of distributions which can see for decay occurring per that is in a radioactive substance per time, depending on what's at that level. So 2 point activity is proportional to the number of undecaying nuclei. As n decreases, activity also decreases. SN is backfire, which is bleaching. One distribution, second definition, activity A equals the rate of decay. A is equal to change in n over the t. The relationship between n. Decay law, n is equal to n naught e raised to the power minus lambda t. You have this example. Important. Activity measurement is essential in medicine. Pressure gauge and relationship monitoring. Next. The reductive decay equation shows that number of undecayed nuclei for activity decreases exponentially with time. Equations. Number of undecayed nucleus n is equal to this. This is very important expression. Expression is going to time instead only on lambda and t. The graphs are example. Yeah? Yeah.
And you see that directly or you must be asked.
It's in terms of the disintegration because we are talking about the number of this is the initial, it's going to be reducing as time goes. So it's inverse. Example, sample has 10 naught equals to this nucleus. Then and this equals to 0 is 1 per seconds. Find n after 20 seconds. Then equals to this, and then you add this to get the total number of nuclei. Significance. The exponential decay equation is fundamental in nuclear physics. The imaging carbon dating, nuclear and safety calculations. Okay. Nuclear transformations, alpha decay equation. Alpha decay occurs when the constituent nucleus emits an alpha particle, which is the 4,2He nucleus, 2 protons plus 2 neutrons. Key features: mass number, A decreases by 4, atomic number A, and it is connected to this speaker. So, another equation, AX is given as this. So, examples. That's cut out. That's stop. So yes, atomic number Z decreases by 2 and occurs in heavy nuclei 8 greater than 150. Alpha particles that have low penetrating power but high ionization power. Also, general equation, this is the general equation where AX is equals to parent of stable nucleus, and then we have your daughter nucleus there, and also with alpha particles. Beta minus decay occurs when a neutron in the nucleus changes into proton, emitting an electron and an antineutrino. Key features: mass number A remains the same, atomic number Z increases by 1, neutron number N will generate to give proton numbers. So beta particles have moderate penetrating power and ionization power. General equation is this. So quark transformation at nucleon level. N odd we later become P or UD, that is unit mass. Then we have electrons here and another electron here. So the point is that initially what and how they might arrange themselves might not be like this, but every of these particles can rearrange themselves to form another existing particle in order to either annihilate themselves or cancel out another existing particle. A quark can arrange themselves to become a positron just to cancel out an electron. Do you understand? If an atom has an electron, the atom has the ability to also use a subatomic debris, that's small uselessness, gather them up and arrange them in an organized form that will mimic a normal stable particle. So if what they want to do is to mimic an electron, you can mimic an electron and position. The position is also an electron. We'll just cancel out. I'll just cancel out the effect of that sense. No less. So the time of decay move apply up the periodic table and helps the stabilization of the neutron-rich isotopes. Next. Beta minus decay occurs when a neutron in the nucleus changes into a proton, emitting an electron beta minus and an antineutrino VE minus. Key features: mass number E remains the same, atomic number Z increases by 1, neutron N becomes proton P plus electron plus antineutrino is what we can take reversible form to form back what you have there. Of course, in the neutron-rich nuclei. Beta particles have moderate penetrating power and ionization power. We went forward, I'm not done. Right, so general equation. They're just moving. Move forward. Zero. Next. So these are key features as usual. This is an electron of the reaction. Quark transformation from a nucleon level. You have general equation. but this is positron and electron neutron. So significance, beta plus decay moves nuclei down in periodic table, lower Z, and is important in stellar nucleosynthesis and PET, which is positron emission.
Any other difference?
Plenty. For which between one?
The beta plus and beta minus. That's the negative electron and positive electron.
Yes, there are plenty of differences.
What are the differences?
Their charge is different. So the way they respond to electrical field is different. Their magnetic orientation is different for the fact that they have different charges. So the way they will deal with magnetic field is not the same. They have a different number of atomic mass. So they will not be the same. My next. The first thing is the only thing that's changing here is this. Let's go. Gamma emission. Gamma emission occurs when the satellite nucleus releases excess energy by emitting a gamma ray without any change in A or Z. No charge in mass number A or atomic number Z. Nucleus goes from an excited state to a lower energy level, to a lower energy state. Emits high energy electromagnetic radiations. Gamma ray have very high protecting, very high penetrating power, but low ionization power. General equation is this: gamma photon. 0, you have this, and energy level, you have this, and they fall from high energy level to low energy level. There is a release of a photon. This represents excited level and ground state. Many heavy nuclei, yes, they can go. Yes, they can go.
What will happen?
They will be doing absorption spectrum. Many heavy nuclei ejected through a series of transformations. You have things like this: alpha, beta, beta plus, EC, and gamma. Until the stable nuclei is formed, called radioactive decay series of families. So these are some of the major radioactive families. I can start with this. Characteristics of a decay series. Begins with a heavy unstable parent nucleus, proceeds through a sequence of A, B, EC, and Y decay, ends with a stable, non-radioactive nucleus, useful in geochronology. Okay. A nuclear reaction occurs when a target nucleus is bombarded by a particle, leading to the formation of a new nucleus and or particles. Okay? Basic forms. These are the basic forms. Where X is a nucleus with mass number A and atomic number Z. Left side equals to reactant. Projectile plus target. Right side equals to product. N plus this equals to this. Same thing you have around it. Type of nuclear reaction. You have these types. And description. You have this. For example, particle induced. Projectile, we have neutron program. You have target, then you have position. ATC, so many of them they hit targeted nucleus. Then they project. This one is capture. They project, we capture by nucleus and all. And so many of them, different types, can always go through. Always go through. Then which one again do you have? Which one again do you have? Fission. Heavy nucleus split into two light nucleus. You have fusion, two light nucleus combine to form heavier nucleus. The house foundation, high energy particles knock out several electrons. That's what it is. So, we could equivalent to the next energy release. Q greater than 0, value Q less than 0. The nuclear reaction. Definition Q, total rest mass energy of reactant, and total rest mass energy of product. For that was interpretation. And this interpretation. Energy diagram was like this. We understand energy diagram. Some are for exothermic, some are for endothermic. So you have this, one of these units, masses in driving, in atomic mass units, where one is equals to everyone, 5. Importance. That means whether it's solid, solid reaction is energetically possible. It means energy carried by kinetic energy of products, and they are essential in reactor physics and astrophysics, as well as in nuclear technology. Observation of mass number total mass number before goes to total mass number after. The reactant is equal to the product, for example, 1H plus 2IH plus 2HA 4 2 plus 10. So, on the left hand side, you have the total of 5, and on the right hand side, you have the total of 5. And then they are balanced. Conservation of energy. Total energy before is what total energy after. So that's why you have this. Conservation of atomic number Z. Total atomic number before equals to the total atomic number after. Example is this. So we have this left, we have this right. Conservation of momentum. Total momentum before is equal to total momentum after. Alright. Conservation of charge. Total electric charge before, electric charge after. This key takeaways. Nuclear cross sections. With nuclear cross section is a measure of the probability the nuclear reaction will occur. Cross section, this is the effect target area that the nucleus presents to an upcoming pathway. Units, SI unit, square meter. With a common unit band B, one band equals to 10 minus 28 meters squared. 1 milliband B, we have this. Okay? So, from there, you can use them. Type of cross sections and total cross sections. We have the total, we have the elastic, kinetic, we have the an absorption. Okay, type of cross sections. I've mentioned them, energy dependence, mentioned them, diagram, and all mentioned them. Formula, and formula to go through. Okay, I think it's 1 hour, I need to rest. Have you infected it? have nuclear reactions. Then we're talking about definition. Look at cross-section. I did it for slides. Cross-section is the effective target area that the nucleus presents to an incompatible. Formula is this. Yeah, this is cross-section. And then we have the diagram, the geometric picture. Units, formula, type of cross-sections, types, symbol, and descriptions. And we have energy dependency. Importance. Okay, so this one's what do you have the reaction threshold energy. Reaction threshold energy. The threshold energy is the minimum kinetic energy required for a projectile for a nuclear reaction to occur. Concept: if the projectile energy is below a specific amount, reaction cannot occur. Threshold energy formula in laboratory film of that. Okay. So we talk about reaction threshold. No, nuclear. It's nuclear. So the concept because the Q value cannot be supplied. Okay, next. Discovery of fission. Nuclear fission was discovered in 1938 by Otto Hahn, Fritz Strassmann, with the theoretical explanation by Schmittner and Otto Frisch. Key event: in December 1938, Hahn and Strassmann bombarded uranium nuclei with neutron. What's the problem? Okay. I thought you asked the question. Instead of heavier elements, I thought you asked me a question. Instead of heavier elements, we found lighter elements such as barium in their products. Mr. Mettner and nephew Otto Frisch explained this by proposing that the uranium nucleus are split into two smaller nuclei. This process was named nuclear fission. The experiment neutron to give this, then you have chemical analysis to give lighter elements. So there you have scientific impact demonstrated that heavy nucleuses can split into two medium mass nuclei, release a large amount of energy, open the door to nuclear energy and nuclear weapons. So mechanism of nuclear fission. In fission, a heavy nuclei absorbs a neutron and becomes unstable. It splits into two lighter nuclei, releasing neutron and energy. Neutron absorption. The first step in nuclear fission is that the neutron absorption. A slow neutron N is absorbed by a heavy neutron. And then you have something like this. There's formation of compound nucleus. The nucleus becomes excited and forms a compound nucleus. 236 nu into 2. Splitting is the next level. So after nuclear absorption, the formation of compound nucleus, then splitting is the next level. The compound nucleus becomes highly unstable and splits into two fragments. And we have neutron emission and energy release. 2 to 3 neutrons are emitted along with gamma rays and a large amount of energy, such as minus 200 MeV. So that's the arrangement of the nuclear fission. So fission releases far more energy per unit mass than chemical reaction. Okay. The most important and widely studied fission is that of uranium-235 when it absorbs the slow neutron. Okay? Typical fission reaction occurs like this. Product barium, then we have krypton, 3, we have neutron, we have gamma ray, and we have, yeah? What's this? You just what? And energy. So energy release, the mass of product is less than that of reactant. The missing mass is converted to energy according to this, about 200 MeV per fission event. What are possible products? Many combinations are possible, common fragment pairs. So you have, these are examples of such fragment pairs. Key point is you have something like this. And this is just a way for a chart that illustrates such. Next, nuclear fission chain reactions. Neutrons release one fission and cause additional fission leading to a chain reaction. How it works? A neutron causes fission in a 235 random nucleus. Number 2, 2 to 3 neutrons are released. Some of these neutrons cause further fission. The process repeats, producing more neutrons and energy. So this is the chart of this distribution. Types of reaction: type, condition, and description. So you have what? You have some critical, you have critical, you have supercritical. K is less than 1 as conditions. K is greater than 1. K is less than 1. K is different conditions for that is the equilibrium factor of disintegration. So the description here, neutron decreases with time, and that makes the reaction die out the moment the neutron is exhausted. Neutron remains constant, and that's what we call steady state power.
Get to a point that the neutron no longer be existing.
Yes, it will finish. Like the more the distribution is occurring, as it's doing they disappear by following the half-life principle. The half-life will be cutting out like that. That's what will happen until it's exhausted. So on this other neutron remains constant, steady power. On this other end, neutron increases with time, power rises. So that's it. Key points. If the mass is too small, too many neutrons escape before causing further fission. At critical mass, the number of neutrons produced equals the number lost. Above critical mass, the reaction becomes self-sustaining. Yeah, we have illustrations. As of critical mass, more neutrons escape than cause fission, reaction stops. Critical mass M equals to M1. So we now have neutron produced, neutron lost, steady reactions. Factors affecting critical mass: purity of fission materials, neutron leakage, presence of reflector, neutron absorption by impurities. Then you have moderators, which are like slow neutrons. There you have it. So critical mass, supercritical mass. Critical mass is right? Nuclear reactor principle. A nuclear reactor is a control system. A nuclear reactor is a control system in which a sustained chain reaction produces useful energy. Visible fission of this releases heat. The heat is transferred to a coolant to produce steam, which drives turbines to generate electricity. So heat fuel up, creates coolant, then you get to the steam generator, you get to the turbine, you get to the generator, and then they release electricity. Reactor condition, it must maintain critically the K equals to 1. Control reaction rate, must remove it efficiently, ensure safety and shielding. Fission, have heat, steam, mechanical energy, and electrical energy. Reactors use controlled fission to convert nuclear energy into electricity or electricity safety and efficiently. Nuclear fission reactor components. A nuclear reactor consists of several essential components that work together to sustain the controlled chain reaction and produce power. So the nuclear reaction consists of that. Control rods absorb neutronium fuel, usually 325, in the form of railroad or pellets. Okay. Moderators slow down very fast to increase fission probabilities. Then coolant remove heat from core, and then controls rods, made for neutron absorbers, and regulate the reaction rates. Shielding protects personnel from radiation. Fuel, usually 235 joule in the form of fuel or pellets. Moderators slow down neutron to increase fission. To increase fission probability. Coolants remove heat from core, which water and increase fission. CO2 and gas are all these categories. Then you have control rods and then you have shield. So we have the control rods. They move in and out of the core. When inserted, they absorb neutrons. And slow them. And slow down reaction time. The other hand, moderators control changing moderators density or temperature, affect neutron slowing and reaction rates. So you have this coolant control, changing coolant flow, or temperature remove more or less heat, affecting reactivity. Okay, the volume it was capacity. When you add soluble, that's the chemical steam or what you call salting. You add soluble neutron absorbers, which basically water reactors. Reactivity and control. Reactivity measures deviations from criticality. Then is greater than 0, increases. Then P is equal to 0, power, second power. Then P is greater than 0, and so critical. Yes, systems. Applications control rod to allow to shut down reactors. And redundant system ensures safe shutdown even in emergency. Then there are continuous monitoring of nature and temperature and pressure. Key effective control mechanism ensures steady power production, prevents overheating, and protects against accidents. So, we have nuclear fusion. It's a process in which two light nuclei combine to form a heavier nucleus, releasing a large amount of energy. Common fission reactions have deuterium to tritium, then we have deuterium to deuterium, plutonium to boron. So they are general fission reactions. These are general examples of reactions. Energy comparison, fuel, reaction, energy. Energy comparison, that's it. Next slide. Okay, hold on. Okay. The PPH is a proton pump chain. The dominant energy production mechanism is starts by the sun, where the core temperature is 10+7 Kelvin. So, the net reactions. Net reactions. Net reaction there. Solution. Yes.
But they don't use nuclear fusion in nuclear reactor. Why?
Because of the coolant processes. And it's not easy to regulate this coolant. They don't. I said they don't find it easy to regulate their cooling process during the cooling stage. When you enter the coolant, you can't regulate the amount of energy that comes out from the fusion. Main branches of the PP chain. PP1 is most common. P to P to D plus E plus VE plus D plus P. U E PP chain will flow down. So the TP chain is the dormant energy production mechanism. It stands like sun, where the core temperature is 10⁻⁷ K. Main branches of the PP chain, PP1 is most common, P plus P, D plus P, then plus V. D plus P, U E, net reaction. So you have the net reaction. You Now the net reaction. Net reactions. 4P to give you HE plus 2E plus 2VE plus 2Y plus 26.7 in the regular electron volts. That's reaction hydrogen indium plus 2E plus 2E plus. So that's the reaction, something plus which. What? HD.
It's E plus P. Give me D. What's it do?
And then deuterium. Hydrogen is a proton. One proton gives you deuterium. Don't forget deuterium. People chain is the dominant energy production mechanism. It's not like so. Where you go, which is about 7 kilo. Main branches of the chain, TP1, TP2, TP3, TP3, G, C, V. So basically, almost all these proton reactions usually lead to the formation of the D and an electron. But that's not showing us the percentage of that hence we give. These reactions. Okay. So HA is 2E plus 2VA. Plus next reaction 4P HP 2 plus 2A plus 2Y plus 26 NEV. Yes. Next reaction PP chain fluid diagram. So this is the fluid diagram of proton chain flow. There are additions of extra protons to previous existing ones, but that increases the size until there is a proton chain breakdown. So next slide. Nuclear fission, carbon, nitrogen, oxygen, cylinder cycle. The cylinder cycle dominates a more massive stars. This is a cycle is catalyzed to fuse hydrogen into helium. Cylinder cycle steps. Cycle diagrams. So you have C13. If you have these reactions, the example of CNO reactions. So the net reaction 4P to give you helium 4 plus 2E plus 2VE. Energy to give you 26.7 NeV. Features CN and O act as catalyst, not compound. Act as catalyst, not compound. Then next reaction, feature CN and O act as catalyst, not compound. Consume high temperature process. Rate is directly proportional to is very proportional to the temperature. Then we have dominant stars, more stable than the sun. Key takeaways. The CNO cycle is an efficient energy burning process that powers massive stars and contributes to stellar evolution. Okay. Key takeaway. The CNO cycle is an efficient energy burning process that powers massive stars and contribute to stellar evolution. Okay, next slide. Common thermometers, common thermonuclear reactions, deuterium, tritium, 2HI, H1, He42, minus N plus 17.6 MeV. Deuterium, helium, now 3 Di 2IH plus helium. So the thing is, these are just examples of reactions that are associated with this. So energy density. Energy density key takeaway. Yes. Well, it depends. If it's happening to an radioactive element, spontaneous. Yes, spontaneous. Comparison of fuel options. Fuel. We have DT, GD, GG, GD. Yeah. So, pros and cons. High energy output. Low energy, hard to ignite, very rare and costly. So that's it. Energy density, chemicals, fusion, fusion DT. Key takeaway. Thermonuclear fusion has the potential to provide abundant, safe, and clean energy for the future. Thermonuclear reactions occur at the extreme. High temperature overcoming the column barrier and allowing nuclei to fuse. Common thermonuclear reactions, deuterium, nitrogen, deuterium. Then we have energy. We have energy comparison of fuel options. We've run through this. Please let me slide. No fusion to occur. Nuclear must overcome electrostatic repulsion, Coulomb barrier, and come close enough to a strong nuclear force to bind them. Conditions: high temperature must be available with a high temperature greater than 10^7 to 10 residual of Kelvin, so nuclear has enough kinetic energy. Has enough kinetic energy. High density increases the probability of collision between nuclei. Sufficient confinement time, and the plasma must be confined long enough for reaction to occur before particle escape. Low radiation losers, energy losers must be minimized. Then minimized to maintain temperature. To maintain temperature. The Coulomb barrier je vais lui energy drink. The Lawson criterion: particle density, temperature, energy confinement time. If the criterion is met energy gain is possible. Fusion, extremely high temperature density, and confinement to achieve a sustained result. Okay, for fusion to occur, nuclear must overcome electrostatic repulsion. Sincerely, if you have any question, ask. So that falls under the category of electrical charge. When two opposite charges, when two like charge find themselves close to themselves, they will repulse. So even during the degradation of the nucleus, the electrons too can degrade and they will contribute to repulsion. Do you get it? Both. I didn't get to say. And bombs. Nuclear fusion. Not fission. Fusion. I don't like the nuclear energy. This one has nuclear bomb and explosives. So it doesn't criteria. It doesn't criteria. It's Coulomb barrier. Potential energy distance between nuclear potential as attractive. The losses effect criteria as detection. Where n particle density, T is temperature keV, and then energy confinement time. If this criterion is met, net energy gain is possible. Net energy gain is possible. G take place. Fusion requires extremely high temperature, density, and confinement. Yes. Look at this one. ensures that temperature. It gives you a balance of what temperature you need for a particular kind of emission or release of radiation. High potential energy leads to degradation of the atom. And when the atom degrades, the electrons there to degrade on the, what they call it, they call it debris, electron debris. If the atom if an atom gets disintegrated, what do you think will happen? Aside from the nuclear pieces, you still see electron particles. So that electron particles now will be yes, now the nucleus will do its own thing. But if those things are too much, they will inhibit the radioactive, the nuclear. You have radiation, you gamma radiation, all of them can be felt, this can be seen too. It's an explosion. The radiations may not be able to be seen because they are not invisible light. But the damage you will see now, then the flames, you will see the explosion. So, next. Magnetic confinement. Magnetic confinement. So, principle, charged particles spiral along magnetic field lines. Magnetic field confines plasma in a closed region, prevents contact with reactor walls, reducing energy losses. Used in devices like mix and stellar reactors. These are for stars. They are for stars. Advantage: high confinement time, suitable for steady state operation, well understood technology. Challenge: expensive and complex magnets. Expensive and complex magnets. Plasma installations or something. Then require very high temperatures though. I think it's the installment. Next, example of devices. Inertial confinement. Inertial confinement uses powerful laser or particle beams to compress small fuel to extreme density and temperature. What are the principles? Tiny fuel pellets. G minus D is in by infinite on particle beams. The outer layer is instantly ablated and blows off. The inward reaction compresses and heats the core. Target compression process. Then beams and jets. Upper layers of these core compressions. And then functional inversions. Advantage. So, advantage and challenges. Inertial confinement. So, target compressions process. So, we have under the target compression process. Consider laser beams, outer layer blades, core compressions, and fusion ignitions. Target compression process. Basically, a tiny fuel pallet. But done with this. Next slide. Nuclear power plants. Power plants convert the heat released through nuclear reaction into electricity in a safe, reliable, and efficient manner. How it works: fission in the reactor. See, it's fission in the reactor core uses heat. Heat is transferred to a coolant. Coolant produces steam. Steam spins the turbine. Turbine drives a generator to produce electricity. Condenser cools the steam and returns water to the steam. Control system regulates the reaction and ensure safety. So we have main components: the reactor core, the control rods, generator, condenser, cooling system, coolant system, steam generator, and turbines. Typical nuclear power plant layout. So this is it. So key takeaways. Nuclear power plants provide large scales. So by carbon electricity by harnessing the energy released during fission in a controlled environment. So next slide. Pressurized water reactors, PWR. Pressurized water reactors use high pressure water as both coolant and moderators to transfer heat from the reactor core to separate steam generators. Key features: most widely used reactor type in the world, operate at high pressure to keep water from boiling in the primary loop, to provide high thermal efficiency. Yes. So it provides high thermal energy safety for moderator and light energy. Advantage: high efficiency, proven technology, low operating costs, long operational life. I didn't hear you. Advantage: high efficiency, proven technology, is a better technology, it's not very expensive to operate, and then it's a long operational life. Core temperature, primary pressure, steam temperature, not efficiency. PWR is maintained without pressure to prevent boiling in the reactor core, boost safety, efficiency, and power output. Typical operating conditions: core temperature 300 to 330 degrees Celsius. The primary pressure 15.5 megapascal. Steam temperature 275 to 290. Not efficiency. Key takeaway: PWR is maintainable to high pressure to prevent boiling in the reactor core, improving safety, efficiency, and power output. Pressurized water reactor. I have done this. Boiling water reactor allows water to boil the reactor core and the steam produces gas directly to the turbine. Simpler design, single loop, water coil in the reactor core, global pressure.
Reactor you mentioned, are they power plants?
Yes. Yes, different power plants. Steam is produced and sent directly to the turbine. The turbine is not part of the power plants. Widely used for electricity generation. So fuel low rich uranium. Listen. Turbine, like it's part of the heavy industrial equipment they use in generating water, generating energy. Whether light energy, whether helping to support water pumping system or pressurizing the dams so that energy generation is possible. Advantage of simpler design. Typical operating conditions: core pressure to give you 7 MPa. We have the core steam temperature, which ranges here, and net efficiency, which is 30 to 34%. Okay? Fusion reactor. Fusion reactors aim to replicate the energy production of the sun by furning light, fusing light, nuclei at extraordinary or at extremely high temperature to release large amounts of energy. So fuels and deuteriums and tritium reactions will form helium, extremely high, see how high it is, approximately 100 million degrees Celsius. No long-lived reactive waste. Abundant fuel. Abundant fuel resources return water high energy output per unit mass of fuel. Fusion reaction, though benefits virtually unlimited fuel, high energy density, environmentally friendly, normal greenhouse gas. Challenges: strict temperature requirements, confinement and stability, material with whitened nutrient variations, high development costs. Next. Key points occurs when the energy of the region exceeds the binding energy. So when the energy of the region exceeds the binding energy of an electron, produces a positive charge ion and a free electron. Binding energy is the energy required to form bonds. And in this one, they are talking about nuclear bond. And still the same amount of energy you need to break nuclear bonds. This is my. So, type of ionization: primary ionization, secondary ionization, additional ion produced by energetic secondary electrons. And tertiary ionization, those are further ionization by secondary electrons. Examples: N particles cause dense ionization along their paths. Beta particles cause moderate ionization. Gamma rays and X rays cause sparse ionization through secondary electrons. Then you have Compton effect and photoelectric effect. So also pair production. So that's it. Next slide, please. Next slide, please. Attenuation of radiation. Attenuation is the gradual energy intensity or number of radiation beam as it passes through a material. We have that formula there for the attenuation, and then different points. Caused by absorption, strain, and leakage. Intensity decreases exponentially with thickness of material. So in that attenuation, it just the more you go through thicker blocks, the more you are reducing the effect of the radiation because the frequency of radiation will drop. So, well, it is the energy is going to affect. It doesn't have direct effect on wavelength. Wavelength is characteristic to the, like it's more about the identity of the radiation. So wavelength do not just change like that. Although during Compton effect and those first of all, it's not something that's significant. So energy of radiation and that. So the next slide. Shielding materials. Shielding materials is to reduce radiation exposure by attenuation. Yes. Shielding material is used to reduce radiation exposure by attenuation or absorbing and ionizing radiations. Visible properties have them. Common shielding properties have them. Shielding effectiveness or effectiveness. Key takeaway. So that's it. That's it. Next slide. Geiger-Müller counter. A gas filled detector that detects ionizing radiation. It detects ionizing radiation by producing electrical pulses from gas. And ionization due to incident particles or photons. Construction. Cylindrical metal tube cathode filled with low pressure inert gas with a small amount of quenching gas and forward gene. Central wire node stretched along the axis. Window allows radiation entry connected to high voltage through a resistor. Output pulses taken from the anode through a coupling capacitor. Working. Incident radiation ionizes the gas, producing electron ion pair. So the gas gain is high, giving a large.
You mentioned that auto-hand from the definition. If you talk about the definition, and you discover this definition.
Nuclear fission.
Yes.
Okay. What was the nuclear fission?
I said like you discover it because you say like you want to discover nuclear fission. So you discover
Nuclear fission has been, that process has even been in place in terms of backfire because it was doing transportation already, which was involved in bombarding energy. So it was a fusion process. So if I might not be 100% sure to say it was in backfire, but if we trace it, there's a tendency is the one. Because I think it's older than Mercury. So it should be. So, figure another counter. Gas field detector that detects ionizing radiations by producing electrical pulses from gas ionization due to incident particles or protons. So here, there's a construction layout here. Cylindrical metal tube, cathode filled with low pressure inert gas with a small amount of quenching gas from alcohol and halogen. So central wire anode stretches on the axis, window maker and aluminum radiation entry connected. So it's just the setup. They follow this setup and subjected it to a high voltage of about 900. The diagram is evacuated of air, and they only use some special quenching kind of gas that will reduce the effect of the radiations if there are any catastrophic risks. So you have the cathode region there, this place region, and then I think the glass itself was like made up of the anode. So output pulsars taken from the anode through a coupling capacitor. Yeah. So the working principle, the quenching gas stops the discharge and the circuit is set for the next event. Features of applications: detect alpha, beta, and gamma rays. Then we have high sensitivity and simple to use. Then it does not measure energy of radiation. Yes. It don't. Radiation detection, power chamber, a detector that visualizes the track of charged particles as they move through it, supersaturated vapor, leaving a trail of tiny droplets. Principles: when a charged particle passes through a supersaturated vapor, it ionizes the molecules along its paths. The ion acts as condensation nuclei, causing vapor to condense into tiny droplets, forming a visible track. Construction: under construction, have a steel chamber with transparent walls, which is glass, containing supersaturated vapor of water or alcohol, and there's a piston or pump to slowly expand the volume between supersaturations. It's also illuminations from lamps or LED to view tracks. What's the working principle? The piston is pulled rapidly to expand the volume and cool the air. Charged particles passes through living ionization trails. Droplets form along with these trails, making the tracks visible for a short time before they separate. Yes. Principle: the charged particle passing through a superheated fluid causes ionization. The ions act as nucleation sites for boiling, and the pressure is reduced, forming a line of bubbles along particles paths. So, working, the liquid is kept at high pressure, and when the piston is dropped quickly, the pressure falls, causing the liquid to boil along ionized paths. Bubbles form and photograph the particle tracks. Okay, well, I'll be taking my break now. Okay. I have to ease myself. the vectors. Then silicon its own deflectors. Many of these deflectors are found even in the SL. Okay. Organization. So, next slide, please. Next slide. Radiation detection. The best dosimeter. Device is used to measure the absorbed dose or exposure to ionizing radiation received by personnel, patients, or in the hospital. So that's that. Film batch. So that's the principle. Film batch. Okay. Personal monitoring. From batch, film batch. Just an electron current due to radiations. Okay. I'll explain. So, application of radiation detectors, radiation protection of workers, medical diagnostics and therapy, environmental monitoring, and then we have nuclear industries. So the key takeaway from this is dosimeters are vital for radiation safety, for the removal of radiations, Okay. Okay. Type of dosimeters. Something like badge is this. Will also be the design capacity. Then look at the application. Let us know how it is used. Alright. So people use it for personal and environmental use. So that was
Why is it not studied?
what is not studied actually?
Yes.
I studied as in I studied in school.
Why is it not studied?
Like in like I don't know what you mean by what they are not studied though.
I said H is a type of radiation, right? Like doing beta hospital. Why is it not studied it?
Studying what? X-ray.
Yes.
Like the course.
Like as a type of radiation.
Okay, like now, yeah.
Yes.
This time will come now. Now they are talking about dosimeters. I'm not talking about the application of radiation now. Yeah. Yeah.
I think she's trying to say like when you're listing the types of radiation and you're listing alpha, beta, gamma. So why is X-ray not listed? Like no
Okay, I get you. X-ray is a characteristic truth. X-ray is not a ray that comes out from every nuclear material just because it heated something. Actually, it's not just kind of radiation. Do you understand what I said? So, mental monitoring. This slide is too congested. Okay. So it measures ionization and also it measures radiation. That's this pocket horizontal chamber. So there are so many other things that are listed here that are dosimeters. You understand? So what are dosimeters generally used to measure absorbed dose or exposed just to ionizing radiation. So where that was? Seriously. What is this? Are you good? Medical imaging. Medical imaging. Stabilization, carbon dating, radiotherapy, industrial radiography, treatment of cancer. Okay, next. Biological effects. We have the biological effects for this. As I've seen with down those ones.
What's the PT scan?
Many types of PET. Which one? Is it the proton enhanced PET scan or what? Which one are you talking about?
What are the application of with like the word PT scan? What is it?
Which of the? I don't know what this kind of scan I'm talking about. Which of the PET? I didn't write PET. Take it back. Except it's an abbreviation for a sentence. Take it back. But keep going back. Except it's an acronym for a sentence, for a word. I'll be taking it back. Okay. Biological effect of radiation and radiation can damage cells, DNA. Effects depend on dose, type of radiation, and exposure time. Deterministic effects, high doses, causes skin burns, radiation sickness, organ damage, and cataract. Then you have stochastic effects, which can cause cancer, genetic mutation, leukemia, and heritable diseases. Then you have radiation dose units, quantities, absorbed dose, equivalent dose, effective dose, and activities. These are the symbols of all of them. This is where you get the units. For those not clear here, you can go do search. This is Sabiet, do your searches. Then you have the description there. Okay. So, radiation hazard and protection. Radiation safety principles. The foundation of radiation protection is based on three basic principles. Yeah, and they are time, distance, and what they call shielding. Right? So this thing here means as low as reasonable achieved. You want it to be something you can easily study. So, but minimized exposure to time, anything that has to do with radiation. We don't want to stay in there for long. Then we have distance. You must keep a safe distance, following universal square law. Then shielding, protect your shielding. Use proper shielding. Use appropriate materials to block or reduce radiation thickness and density of shield and increase protection. Additional safety practice. Use personal protective equipment, gloves, lab coats, and lead aprons. Work in well-ventilated areas of fume hoods. follow written procedures and safety protocols. All these things are things you should know. Then just mention this already while achieving the desired effects. Okay. Then you have these variations of shielding materials, this variation of radiation types. So there you have it.
Like, in terms of, like when the number of protons and the number of protons and neutrons are equal.
That's when it's stable.
Yes.
Are you worried?
And the when it's stable, when the protons and the neutrons are
Are
equal.
equal.
Yes.
Is that even true?
Sir.
Just give us an example of such. Give us just start from. Start us from elements from 35. Just give us any one from 35. From atomic number 35 up. Well, even that first to 20, I don't think she should be lucky. Zinc. If you type on Google now, you start checking how many neutrons are in zinc and how many protons are in zinc. The gap between these, you will not believe it. So the number of makeup of the nucleus is not what controls the stability of the nucleus. The stability of the nucleus is more about how unchanged it has remained for a long period of time. And what are the things that controls that? We are talking about things like the orientation, distribution of the nuclear particles, most especially the distribution of the nuclear particles. You know that the nucleus, you have proton, you have neutron. And what do protons do? Protons, what they do to themselves is that they repair themselves. So it means that there is a way they generally organize themselves such that that space for such repulsive force to be availably active won't be there, or it will be to the minimum. You get? So if I want to use a two-dimensional arrangement to explain this to you, let's take for instance of these red markers. Positive electrons. And let me just pick these two blue as negative. The most preferred way, if somebody come and arrange these electrons like this, these protons like this, they can never be stable. Why? These two react themselves, these one reacting repairing themselves, and before you know it, the nucleus might even tear, it will even rupture first. That's if you view it as a sheet, not just as a compass colony. But if I now decide that these people they don't have charge, and that's why I want to intersperse neutrons in between electrons. This has solved the instability that comes from spatial arrangement of. You understand? So it's not by the number or all those ones you're saying. Okay. The nucleus is stable. The nucleus is stable. The nucleus is stable due to nucleus is stable due to due to its inability to remain unchanged, and undisturbed for a very long period of time. To remain unchanged and undisturbed for a very long period of time. An unstable nucleus undergoes spontaneous transformation into a stable nucleus. So whenever there is instability, it's naturally supposed to stabilize itself. So please, I'm coming from first. Boss. again. That is what I was saying. It can stop it. Like literally, there is no mechanism of somebody coming to come and rearrange it. It fixes itself. Except it has been tampered with intentionally. The nucleus will not just disrupt. The nucleus is not like the electron. You hear that an electron just fall from orbit and misplaced. It's not like that. So some of the ways now that it can attain such a thing is by instantly engaging in the release of electrons or radiations. Sometimes that's just all it needs to get the stability back. Sometimes all it needs is to absorb radiations. So stuff like that. And those processes are spontaneous. Okay, a nucleus is stable when the attractive nuclear force when the attractive nuclear force balances out with the what? What are they going to balance out with? Balances out with the what? With the host, that's the protons themselves. Do you get? So there's a proton-proton interaction, which is like what is going on between them. There's a proton-electron interaction too, which is they are trying to use to keep their shells and their electrons in check. Which one? A what?
Said that the nucleus is stable when the attractive nuclear force balances out with the words.
When the attractive nuclear force has
Said the nucleus is stable when the attractive nuclear force balances out with the words.
It's not the one I'm saying now. That I'm repeating. I was saying that it balances out. The host is themselves now. They are the host. Nuclear force comes from the protons. And as they are balancing the electrons, they need to also balance themselves. How is it balance themselves? Making sure that what is within the... Because it's attraction that they are doing to electrons. What they are doing to themselves is repulsion. And that repulsion will tear them apart. Do you get? Yes. That repulsion will tear them apart. So that competition is the issue. That's where the stability is balanced. They are constantly competing. There's usually a conflict of interest in they supplying nuclear charge to atom's electron compared to keeping it for their own stability. I don't want to try groups. So, I said that there is constant competition between the repulsive group. What are the repulsive group? That is between the hosts, they themselves, and the attracting group, which is the electron. So we call it a competition between electrostatic contribution to nuclear force containment. You get it? There's a competition between strong nuclear force that's produced by them and the electrostatic force that's they are still part of. Do you get it? This is too loud. That's calculation computation already. Okay. Okay. So, under that calculation, we are just going to be focusing on bondage and mass defect and rate of disintegration and the fact that it is a first order reaction. So, there's something we call rate of disintegration. And there's something we call rate of disintegration. What is that? What does the law state? Anybody? It states that the initial count, the rate, the initial count rate of a nuclear mass is directly proportional to its values. Yes. To the rate of disintegration. Yes. It's just like how the put momentum, the rate came after the first statement. So the initial count rate of a nucleus is very proportional to the rate of disintegration. Yes. So what does that mean? I'm saying n not proportional to the what? Okay. And this is really the constant, what is it? It is. It's the cost. Now the negative is why? Because it follows the first order distribution system. These are the very cool facets. So that's the first thing we want to touch on this. Having known this, you don't have a problem with some round distribution. Also, we also have to introduce the fact that most of it are not. I know that I have told you guys that the n is equal to the n what plus what. So the n is equal to minus lambda c plus and then what. So the n is equal to minus lambda c plus the n naught. You get? So we can start rearranging or doing it like this. So people like to bring in their splitting to one side. I don't know why they like to, I don't know. You know, because we can put in there. It's different. So this is the first order distribution. So, lost. N not over 2 because minus lambda CF is not inherent. True of us, you are also getting the half of it. So what we have to carry the not to the side, or carry this one to the side. Lambda. Which one? I carry this one. I carry this one. I'm calling. And I don't need to do rubbish. What are those? Then open brackets. N naught times 2. And that's considered as quick animation. Then you can do it like that simple. But let's also appreciate this.
So, like I was saying, how is that in this formula now? Half life is equal to 2 over 0.692. Like, can we say half life is equal to in 2 over 0.693?
Hello.
Is that it?
Yes. The source has an activity. The source has an activity. 8.0 times 10 power 6 bar. An activity. 8.0 and The source has an activity. The source has an activity of 8 times 10 raised to the power of 6 backward. Times 10 to the power of 6 backward. 8 times 10 now, raised to the power of 6. 8 times 10 raised to the power of 6. The source has an activity of 8.0 times 10 raised to the power of 6 backward. The decay constant is 2.5 times 10 to the power minus 6 per second. Determine the number of reactive nuclei. The number of reactive nuclei. A source has an activity. Has an activity. The source has an activity of 8 times 10 raised to the power of 6 backward. The decay constant is 2.5 times 10 to the power minus 6 per second. Determine the number of reactive nuclei. 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 So, bring what? Let's bring it. And then, a source has an activity. Do you don't know that thing? Activity of 8.0 times 10 is 1 6 backward. So you're looking for it. But I don't say it's very new now. You know what she does in class? Very, very. Not necessarily, man. You'll be dictating. She'll be waiting for to only write parameters. She'll not write only parameters. Her life is for parameters. And as I tell you, I don't measure the constant. Say human being not. A source has an activity of 8 times 10 is 1.5, of 8 times 10 is 1.6 backward, of 8 times 10 is 1.6 backward. The decay constant is 2.5. This one too used to weight. The decay constant is 2.5 times 10 to the power minus 6 per second. Determine the number of reactive nuclei. I dey shake remember. The last time I slept was on Sunday last week. Sunday last week. Eh?
Tomorrow night it will go.
Can you give me only? Oh. Like, don't worry. I'll call it one more time, I'll tell you. A radioactive source has an activity of 5,000 BQ, backwards. Its half-life is 5 hours. Find the number of radioactive nuclide present. Find the nuclide present. Nuclide present. Because you know I'm coming at the 90 sentence. What is this? So, are you guys not done? So, a radioactive source has an activity of 5,000 BQ. So, activity, we have how many of that there? We're having 5,000 times N. $5,000 divided backward in its half-life. Okay. We don't need to. Okay. A source has an activity of 8 times 10 raised to the power of 6 backward. It has an activity of 8 times 10 raised to the power of 6 backward and a decay constant of 2.5 times 10 raised to the power of 6. Yeah. Determine the number of radiation nuclei. So that one now. Activity something of 8.6 as A 8.6 activity of this. The decay constant is 2.5 times 10. 2.5 times 10. Times 10 is power of minus 6. Okay for me.
Yeah, side. Yeah, side. 3.4 kilograms.
Yeah, God, this is the worst. This is the worst. Honestly, good. The artist source has an activity of 5,000 by night. Activity. Okay, constant. It's half life is this. It's half life is this. I don't know. So, so, okay. So this is the activity of this one. I'm going to put the BQ there. BQ. Mm.
So, what do you think?
Yeah.
What did I answer?
It means I know what they ask. It means I know the one they ask. Don't know that not the one they ask. One more.
Next question.
Okay. I don't know, is that my phone? Il m'a dit à la vingtaine. Pourquoi il a mis le conflit? Non. L'autre. I know how many. So we're back. We're back. So a tissue absorbed 2.4 joules and receives dose of so we are going to be solving these questions. And this a radioactive sample initially contained 1.8 times 10 raised to the power 20 nuclei. That's initial. The decay constant is the radioactive sample initially contains 8 times 10 raised to the power 20 nuclei. Yes. 8.0 times 10 raised to the power 20 nuclei. The decay constant is 2.5 times 10 raised to the power minus 6. 2.5 times 10 raised to the power minus 6 per second. Calculate the number of nuclei remaining. After 5.0 times 10 raised to the power minus 5. So you can use the exponent method to approach this question, or you can spread it out in the equation method to solve this question. So what are you talking about? What about is the n not e is lambda t to solve it, right? So what would that give me? N is not equal to what? Final answer. Okay, n is equal to
8.0 times 10 raised to the power 20.
e raised to the power
2.5 times 10 to the power minus 6 times 5 times 5 times 10 to the power 5.
So when you put that into your calculator, you get 2.29 times 10 to the power 20.
Not 2.2 minus 10 to the power 20.
Yes. A source has an initial activity of 5,000 BQ. Its half-life is 8 hours. Find the activity after 24 hours. Half-life is 8 hours. Find the activity after 24 hours. So we're looking at Let's determine number of half-lives. So this one now, initial activity.
So initial is 5,000.
Yes,
Then your time
it has a half-life of 8.
8 hours.
8 hours.
Then your time is 24
It's
hours.
for energy for final
For
activity.
writing n over n plus 1 over 2 you have
2.
The answer is 65.
Thank you.
Next question.
Radioactive isotope has a half-life of 6 days.
Half-life of 6 days.
Mm-hmm.
Okay.
Initially, it contains 3.5 times 10 to the power of 18.
3.5 times 7 to the power.
18.
Yes.
Okay.
Atoms. Calculate the number remaining after 15 days. Calculate the number remaining after 15 days.
After 15 days. After
15 days.
15 days. Okay. So that's so the answer is 6.18 times 10 to the power 17.
Yeah?
6.18 times 10 to the power 17.
Did you use Zephyrs method?
I use n over n plus 1 over 2
N over N.
n over n plus 1 over 2.
Wait, 6 was 1.
N over N
Over
plus
n plus 1 over 2 raised to the power
Oh, 2 over 2. Zephyr. That's Zephyrs.
yes.
equals to 1 over 2 t over t over t. Yes. That's I'm looking for n over
5.
3.5 times 10 to the power 18 equals to 1 over 2. Okay. Raised to the power 15 over 6. So everything plus multiply n is equal to 6.187 times 10 to the power 16. Yeah.
A radioactive source has an activity of 900 becquerel. 900 becquerel. After 4 hours.
After 7 hours.
After 4 hours. The decay constant is 0.12. No. See, the radioactive source has an activity of 900 Becquerel.
Okay.
Activity of 900 Becquerel after 4 hours. Its decay constant is 0.12 per hour.
0.12.
Per hour. I'm being slow.
Now, I'm looking for the final activity.
That is
The answer is 556.
0.9. The answer everything is 556.9.
okay.
Is e raised to power minus 0.12.
So, A is equals to
I don't.
A
I don't know what you're saying. I don't know what you're saying. I'm good. Oh, yeah, I'm not doing that one. Next question.
Next question.
The activity of a radioactive source increases from 5.0 times 10 plus 7 Becquerel. The activity.
Okay. Radioactivity.
The activity of a radioactive source
Okay.
depends, it decreases,
Decreases.
yes, from 5.0 times 10 to the power of 7 Becquerel. So 1.2 times 10 is to the power of 7
So
Becquerel.
1.2.
1.2 times 10 to the power of 7 Becquerel.
So 1.2.
Confining
The final one. Okay, so what are you looking for?
What's when you can find it? Pity you.
This one is so what are you looking for? What are you looking for?
The decay constant now. It is of you try test you try test. Pity you. Yes. I will see that one. Decay constant. Thank God. Now, see, I dey feel for old people. I can remember my dad too. Come on, he's a professor. That time when he was old, he will not be slow. I can't do that. Sir, can't you jump step? Jump this step while you're writing. Oh, good. So what method are you using? I'm not like this normally. Oh.
The degree constants is 0.047.
The next question.
That's okay. It's me that's calling the question. My duty, because I don't be answering it. A radioactive isotope has mass equal to 2.5 grams.
The reactivity.
A radioactive isotope. What's that? Okay. A radioactive isotope has mass equal to 2.5 milligram molar mass. Mass equals to 2.5 milligram molar mass. That's 210 gram per mole. Then half-life equals to 138 days. Determine its initial activity.
So can you repeat the question again?
I'll repeat it now, man. So, how many times do you want to repeat it? Just so maybe right here.
Okay, so you said it has a mass of 2.5 milligram. As the molar mass measured in milli.
210 gram per mole.
210 gram per mole.
Then half-life 138.
210 gram per mole, okay.
Half-life 138 days. Half-life 138 days.
Half-life 138 days.
This two combination is still the best I know. So the best in loot. So the best in loot. This one is going to be the best in engineering department. So I started topping them. The research exam they wrote 98, 94 over 100 for biochemical biology. Medical biochemistry. 0, 7, that's for the neutron. This is neutron. Yes. 1, 0, 0, okay. This is 1, 1, 0, 0, 8, 6, 6, 5. Alright. Where is it? I don't.
What atomic mass unit is equals to?
It's equals to for helium.
Oh, like general, that time of
Okay, 931. Yes, sir.
the mass effect for mass effect is 0.030377. The mass defect.
It's correct.
Okay, let me get back the thing.
That's you said 0.0307.
Yes. The binding energy is 28 point
13 M.
AM.
Zero, zero. I'm if you call. That number I gave to you is 931. I said 931. 8.5. Okay, you use 0.5. I do not know it's 0.5. You can just let me ask.
Shall we solve another question? On the same aspect.
Sorry. 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 Huh? No. Calculate the binding energy. Nucleon. Calculate the binding energy. Nucleon of 60. Sorry. Nucleon of oxygen. Mass number 16, atomic number 8. Giving. How's this written? Tell right person first. then atomic number 8, then number 16. I think look at this one. Let's have a look at this one.
So what's the mass?
Mass of the proton.
Yes.
Mass of proton is mass of proton. It's not positive. No, that's not true. What do you mean? To be this one.
So should we leave that question?
It depends with how to do something. I think mass of proton is for everybody. It's general. The formal mass of proton is still used. Still
So
mass.
what about the mass of the oxygen atom? Explain for what?
No, you use mass. Oxygen on is at 60.
Just
Is that 60? Is the 16.132. The original one. That's one what you can't compare it to affect.
yeah.
It's in between. It's straight. You have speaking fast.
What's the 8.06?
Which one is the one?
The mass effect.
The one? Is it the
So, like, you said you find the mass effect is going to energy by nuclear.
okay, the mind effect.
8.06.
No, what I'm saying is different.
It's what?
They left it here in if you are getting it in MVC, you got it in MVC. If you are getting it in MVC, you are calculating it in energy. It's what before. It's what it in
So can you recall your value again?
I need coin values was it's what because you don't use values I do. But let me look at what I have here. 1.007825. 1.008665.
What about oxygen?
Oxygen. No. What do you rate at potency? What do you rate 15.994915? Yes, no.
Had also been report said it was 16 database for the mass number and proton atomic number.
16 8 I just said that.
Eh?
I think the mass number for oxygen. No, when I said 16, I meant 16 is up 8 times.
Yes.
But the real one, that's what we use for the atomic
That's
mass.
that 15 point.
Yes, because it's in air. It's in unit mass. Next thing engineering student, I told you, next thing engineering student to such can start preparing to prepare the mentorship. Yes. This is the program number one. I'm going to go and bring them. Don't worry, I'm giving you a job.
So the mass effect, is it 0.6337?
So I'll give you 100 naira, but I'll call your mommy and greet her. She'll not give me my money. It's small thing.
Is it 0.6337?
What 0.137 something. Did you multiply it by this? You know, I suppose to multiply. Let's say, come see the question by yourself. It's me myself. I don't know if I know what to again. I'm confused. There's nothing that's not confusing me. It's very good. Like, are you good? Are you good? I'm looking hopeless now. Don't talk to me. You want him to talk to me?
I'm not going to swap it.
Hello.
How can we define binding energy?
It's
When we say
the
that it is is it a minimum amount of energy or it's just an energy?
just the
It's just
energy. Just energy.
okay. So it's energy that is not either separate or
Join.
combined.
Yes.
Okay. So now we ask the question like that. So sir, we can ask a question like that now because now exactly.
Yes. Yes.
Next question, sir.
So now we solving more questions already. Yeah, we solving another question, another topic.
Um, what's that? 9 hours left.
So what if we ask, like, between nuclear fusion and nuclear fission, which one takes more energy compared to the other?
Compared to
The other, like fission or fusion?
fusion.
Fusion.
Fusion. Yeah.
So it takes more energy to fuse small masses compared to break it down in large mass.
Yes.
Okay, so
Sleep. Go.
In nuclear fission and fusion, which one is used in making atomic bombs and hydrogen?
All of them.
Both of them. How do they make the atomic bomb, nuclear fission or fusion? Because one of them is separation, one of them is combination. Sir?
That means true.
Yeah.
One of them is separation. You have to digest what you're saying.
We have to.
Meditate on it.
Okay. Okay.
I don't know.
how velocity?
So, what topic are we doing, sir, when we start?
Body with the activity.
When you start? Like when we come on board? You should do it, I don't know.
Eh?
So it could be like, it's really testimony lectures.
Okay, so should we like move on to the next thing? That's should we like move on to nuclear and apply? Should we?
Sir, under applied physics, that's where we have lasers, right? What is happening for lasers, sir?
Light amplification.
Sir, can you answer?
Yes. Light amplification of simulated
Can
electron.
hear you?
Hello.
Hi.
Check.
Sir.
Hello. Yeah.
So what's happening for laser?
How much you give if I get it?
Eh?
How much you give if I get it?
Eh?
How much you give if I measure it? Stop, man. Wait. You just don't disturb me. I want to rest. You have to rest. For 2 minutes. 1 minute. Sometimes you don't do
So
it.
sir, what's the full meaning of laser?
Sir, what's the meaning of laser? Sir.
I
There are types.
What are the types?
But sir, we don't know the type.
Jet pipe, jet has been existing before the event of extreme.
What can you share from that line? Like physical lines that
That explains transition of electrons from one orbital to another orbital.
Okay.
Each line is an energy. Each line is an energy. The collection of the line forms a series.
Okay. So,
So actually, it's best called Fraunhofer series. Like Fraunhofer set of series. Because it is each of those Fraunhofer that will form the Lyman series, the Bellman series, all those things.
okay. So,
talking about
ultraviolet,
You guys should go and open podcast. Pay people to come. Pay open podcast.
when you're talking about ultraviolet anatomy, what can we relate it to? Are we relating it to black body radiation?
That is the first experience of black body radiation. That is the first experience of black body.
So, when we're told to explain the thing, ultraviolet anatomy, what, like, in what literal words should we explain it?
Explain it in form of the graph. Explain that colors that have higher intensity usually used to peak, PAIK, used to peak at lower wavelengths. Because of that, scientists felt that no matter the intensity, that all bandwidth of wavelength will appear visible light, in as much as they are visible light, regardless of the intensity. What causes the intensity? When they subject it to experimentation, they heat up they start the heating process. The last radiation in visible light, they couldn't get the peak. The peak was not measurable. Wasn't measurable. Was not measurable.
So it was too high.
If that's what you want to call it. This thing again. Let me put it down what before my move. Who knows who is last?
Okay. So, sir,
So sir, for like when like an object is moving on a smooth surface at an inclined plane and there's no force acting on that object to move it up. What's going to be the formula for the resultant force acting on the object? The resultant force is moving on a smooth surface and there's no force acting on the object. Is it going to be like the force of gravity
On a smooth surface.
on the smooth surface? Yes.
And then there's no force applied.
There's no force applied.
The object is coming. It's coming as a result of component of gravity.
Component of gravity.
Yes.
What about when it's on a rough surface but there's no force acting on it? What will be the component of the resultant force?
You can't. It depends on the inclination at that point. If the inclination is enough to spontaneously overcome static friction, let me just say limiting friction, to start moving, giving the no applied force
Okay, let's assume it was moving.
to here.
It was moving downwards. There was no force applied. It was moving downward and it was on the rough surface. That means the resultant force will be the additional force because the force of gravity. And
That's where the controversy is.
that's what was.
That's where the controversy is still now.
So
Because
it's minus.
in that case, some scientists believe that the book that body is not in motion. It's not an actual motion. It's moving related to the surface of the friction, the frictional
The frictional
table.
effect of the surface.
And something like that.
sir, what can you say is an evidence for matter as the real?
For marker,
Matter. Like, what's an evidence that matter behaves as the real?
as light, give as a wave in me, or electron.
Electron.
The fact that it deflects.
So can we call it diffraction? Direction diffraction.
I didn't say diffraction.
Deflection.
Deflection and diffraction are not the same. No. You are not here. Like, why are people trying to educate? Who can handle the voice? This people, like, this one is the music.
How polygon flow works.
Keep arranging all your vectors in a repeating head to tail order. I know they do. Why are you shouting? Why are you shouting? Why? Why? Like, why just shout things? Because head to tail, so that the resultant now become the one that disorganizes the other. Or some people say it uses its head to connect its tail to the tail of the first wave and its head to the head of the final vector.
Okay. So, when light moves in a straight line, what can we?
Bego.
When light moves in a straight line, what can we call it?
Well,
Moves in a straight line.
in the straight line.
What
Linear motion. Linear motion.
have I read linear propagation?
I was waiting for you to see. I want to see what you were saying. I mean, you just chill. Because I've said in the class already.
So like in terms of when
The motion of the comets whenever they enter into the Earth magnetic field is what kind of motion? The motion of the deflection of comets or asteroids whenever they hit the Earth magnetic field is what kind of motion did they feel? Linear. Even in a magnetic field. No. No. You can't just say curved. Do you know how many curved are there? Curvilinear motion plenty. I start mentioning. Score.
so what's it?
So you are building up 5K. 5K going. If you get it over 5K, it's been like It is the amount of energy you need to stop that electron from jumping out. Let me put it your own way. So it is the kinetic energy.
Okay. Opposite of the black body. You said something about emitting and radiating,
Yes, not reflecting.
not reflecting. So, if it's not a black body,
Is it time already?
if it's not a black body, is it a white body?
Do you feel that black body is about the color? Do you feel that black body is about the color? propagation, on the basis of source, on the basis of, you understand? You state it like that before you start mentioning it. Because that's why we do the white thing. When the transverse and longitudinal, you can't use it as a general way to classify because electromagnetic can deal themselves. Exhibit as what? They exhibit as what? Transverse. Answer your question that the exhibit as what? Exhibit as what? Mm-hmm. These ones are even crazy transverse ways. It's like double transverse because you have the magnetic field existing as a transverse, the electric field also transversing. That's the transversing now. What? Good for food. Good. No, not wrong with that. You see, kinematics. Do you want to do kinematics for how many hours? 12 hours. So you the kinematics 12 hours. You'll be solving like that. When I call the question, don't solve. Don't solve. Today, Steph, can you sit down and do 5 information topic? Can do 5 from each. See, I told you what I'm going to do. 5 from each topic. So when you go, I'm taking it. So that means a total of 1 minute before the night teach. Wait, let's say 10. What else? Think what? Alright. So we're going to be solving questions, running through questions on all aspects of physics. So we titled it Analysis and Problem Problems. Okay.
That you told me we are solving questions.
Topics, like we are solving questions, everything. So I want to check out how many cycles we can make. Let's go. Question 1. The speed v of a wave, the speed v of a wave the speed v of a wave traveling on the surface. When we get to sound wave, remind me, let's use big Laplace equation. The speed v of a wave traveling on the surface, rather not through, on the surface. Of a deep water. Depends on A, gravitational field. They don't write that, they just dot. Gravitational field. Density of water. Wavelength. The speed v of a wave traveling on a surface or on the surface of a day, traveling on the surface of a deep, So what am I doing now? Have we started? I'm moving at fast pace, so speed v of what is it? Where is it now? The speed of
Dimension of velocity.
eh?
Dimension of velocity.
Yes. Because of this position. It's even gravitational acceleration. All right, let's go. Well, let's go.
Are we using that method? Yeah, that method of finding.
Rayleigh's rule. Rayleigh's rule. Rayleigh's method. Follow me. Which constant?
Dimensionless constant.
Okay.
Dimensionless.
You can tell you how to put it, you can tell you how to put it. is my breath. That sound, the sound you're hearing of me. And then I'm breathing. So we compare our T. Okay. Hello. So we compare our T as well. So left hand side we have T minus 1, which is equal to T raised to power minus 2Z. So it's very easy to get our dimension of M from our Y from M. It's clearly seen to be Y equals to 0. Then we can get our T easily as you can see T minus 1 equals to T minus 2. So obviously that's what equals minus 2Z. That is 1. So finally, let's work on that on the L. Okay. What is Z? Okay.
L1.
No.
Supposed to be L1 equals
Where?
so the L part, L1 equals to L is not minus.
I don't know, I already saw some of this place. That is Z minus 2. All right. Equal to 1. Minus 3 over 2 is equals to 1.
That minus 3y equals to minus 1. That's, yeah,
Okay.
I'm sure.
See, let's see this thing.
For that part, your
There
N,
was no Excel.
yes, your
This is from here now. Start from here.
size, that is a mistake.
It was the last one.
Y.
It was supposed to be
You
X.
have y equals 0 and y equals 1 plus 6. So you have y equals 0 and y equals 1 plus 6.
Where's the duster? Let me see. So I guess I have M0, 1, 2.
L is power 1 equals Lx minus 3y plus z. Lx minus 3y plus z. Therefore, that's 1 equals to x minus 3y plus z. That's 1 equals to y equals to 0. So that's 1 equals to 1 equals
Yep. Now, when they talk nonsense, you still talk. There was nothing I could do. I skipped. I did not even open here in the first place.
like we already had y equals to 0 there. You're just putting down.
In the former one, the former one error happened here.
This is what I'm saying. We already had m this equals 0 equals to m equals y. So y is equal to 0. But that for m, where we had 1 equals to
Is
m.
it the one I've cleaned? Is it the one I cleaned already before?
I don't know what you just did. Like I'm telling you. That we had where we had y equals to 0. We'll have just instead that place 1 equals to x minus 3 0. So that we simplify it and have 1 equals to x plus z.
Is it not the same thing? Is it not actually the same thing?
Yes,
That's the answer. It's not like if you put it get an equation, then you will wait again. For NLT complete. So thus sub x as 1/2 and y as 0. Okay. So we have one equals to 1/2 minus 3 into bracket 0 plus z. And you realize 1 is equals to z minus 1. Z is equal to half. So we have z is equal to half. So automatically v is equals to kg raised to the power of x, and then mu This is power of y, as well as lambda is power of z.
Because that.
I don't get. Okay. Question 2, the time period T depends on
L.
G and M. So T is equals to K, L, X, G, I, and M, Z. I mean M0, L0.
Okay, so okay, so
L, L, X, okay.
that's
So therefore,
X equals to X equals to 1 dot.
so K,
That's
L,
A L raised to power 1 dot. G raised to power minus 1 dot. And Z raised to power, okay, sorry, N raised to power 0. That's TK square root of L over GS. Yeah.
let's see how console.
Don't get money. Question 3.
The drag force F acting on the sphere. So
Okay. Okay.
I just saying the next Alex. Yeah, I'm confused.
L is for minus 3x, Ly. Is for
T raised
minus
power minus
y.
Let's go to T raised power
Minus
minus
y
y.
or minus 1.
That's K
Okay.
M. Right?
Oh,
Yeah,
plus
plus
z.
Z. Plus, no.
No, minus 3x
3
plus
minus
y plus
3x
z.
plus y plus z. Then for F, we have that's F. Of course, MM equals
MLT minus 2 is equal to MX L minus 3 S plus Y plus Z.
One plus 2 minus 2.
Hold on. So we're having Z minus 1 equals to 1. Z is equals to 2. So we're going to be substituting back into the original expression,
yes,
which is this. So we're having the proportionate expression being expressed as F equals to K density X, and our X has been gotten to be 1. And then we have V, where our V is now 2. And then we have our V to be square. So that's when it's up. So this expression here is equals to K rho V squared E squared. So that's for that one. So we have Lx power. So the power required to drive a propeller depends on so we have solution. So we have P as the dependent variable, which is power, and power is what that's work done or time taken. So energy. So we're having L to T minus 3. Confirm. So then we have N equals to, it's a confirmed power. The work you are supposed to be doing, not do. Rotational speed N as propeller diameter. Density. So now we've stated out the density, the dimensions. So what are we going to be having? We are going to be having the dependent variable power, which is directly proportional to these remaining parameters. So we have N, D, and rho. So label them X, Y, and Z. Good. So we have power now is equal to K. The N is this. The D is ordinary L. And lastly, the other one is MZ, M-3Z. Very risky.
So power is ML to T minus 3.
ML2.
I'm making it now.
Did you check it?
Yes, ML to T minus 3 equals to KT. Equals to KT minus 1 LY MZ. KT MZ first. Then Ly plus Ly minus 3Z C minus 1. Then for N, we have 1 equals to, for C, for M, we have 2 equals to Y minus 3Z. 2 equals to Y minus 3Z.
It's up. I thought there was a split, I didn't heard it. I said, now this is up. So we are now having here, for L, I'm having L square, Ly minus 3Z. So that gives us 2 equals to Y minus 3 is bracket 1. So it's now equals to Y minus 3, 5. Okay, so
That's 2 is power minus 3Z.
that's the one lost there. It stopped. Minus what?
Minus 3Z.
The last two.
T raised to power 1 equals to T raised to power minus 3Z.
Like, you're seeing what you yourself, you're just doing.
It's T raised to power minus 3 equals to T raised to power minus 3.
You should just shut the face.
There's an error.
You just to the face. Wait, see. This is.
There's not supposed to be any T at the
This
other
is.
side.
This. T minus 1. L. So it's just T minus 1 at the day. Yes. How many dimensions have we got? In 2 dimensions. Z and Y. That's how it's good to. Just the play. Yeah. Fluid density. Fluid density. Z. Impeller diameter. Okay. Describe this measure. I swear. Some relationships, I don't know. That's why. That's why this thing now, this relationship does with it. This breathing, I standing here. I know what I'm saying. I already tried it in my head. It's not with it. What's that? Eh? You usually sleep. Eh? Okay, wait though. I said my brain is doing small. Let's just shift it back. Let's just. Eh?
What do you want?
Okay, so
I'll have prepared you guys. You know what to ask something on the board already? What? Lower. It's okay like this, though. It's okay like this. Is it good? Okay, sharp. Good. Continue. So we're going to Buckingham Pi theorem. We're going to Buckingham Pi theorem now. Is there way these people can actually play like somewhere in the bush there? Like you have to in that corner. Bless, why are you there? What's her name? Deborah. Oh. You see this like, oh shit. Come inside. Yeah, come inside. Okay. I forgot.
So it's
This broken and bite you. Let's take charge of the voicing.
so the diameter is
So we have the velocity. So are you ready for these ones?
viscosity.
So what's the diameter now? Pressure drop, starting from pressure drop. Pressure drop, change in P. Pressure drop is what?
Pressure is ml minus 40 minus
ML.
ml minus 40 minus
Okay.
your diameter is sigma L. Density is ml minus. ml minus viscosity. Diameter is L, sigma L.
The only one. So cast call it down, pipe diameter, number G. Don't confuse person. Okay, number G. So D is L, then we have pipe length L, SCLT minus 1.
Viscosity. Viscosity.
So when you are,
Viscosity is not
where is it? Oh,
viscosity is L, ml minus 40 minus 3.
split type for density.
Density is ml minus 3.
Uh,
Viscosity is ml minus 40 minus 3.
T minus 3. I told you to take out my do something. Now is it T minus 3?
Viscosity is not stress over the velocity movement.
So it's really minus 3. I need to check something, check it. So yeah. So we pick a repeating variable, 3 repeating variable, before then how many fundamental, how many variables I want? So 3, 4, 5, 6. So having n is equals to 6 and m is equals to 3.
It's not pressure, length, density, viscosity, velocity.
Viscosity velocity.
It's diameter,
Uh,
velocity. Then m is equal to 3. Then your pi is equal to 6 minus 3. That's equal to 3. So we're picking p values. That let's pick density, maybe density, velocity, and length of pressure. So pi 1 equals to f, or f equals to
real VD.
rho v.
It's a common constant arrangement.
That's f open brackets, mm minus 3,
Yes.
lt minus 2. And velocity is lt minus 1. That's mm minus 3, lt minus 1, and l.
dot drag force. I put them in minus 3 now. You've seen it plenty
Why
times.
is it first? There's no first.
It's not force, it's function. It's not force, this is function. Pi 1 is the function of this 3 repeating variable. Dot
Dot the function.
dot the independent variable.
That
So,
means put a degree and then you can also set your answer.
yes,
Either that thing that is not put in those things.
yes.
So we can as well put this first and so by what is equals to f open bracket fm minus
What is equals to
f open bracket fm minus
so we're having real is what? ML minus 3. Everything is power what? S. Then we have LT
L
minus 1.
minus 1
Everything again.
y y and L with power of Z. Dot change it. Please ML minus MM minus 20 minus 2. Okay, so we have phi 1 equals to M1 plus 1. So you're having
So we now have okay. So we now have
so you're having mx plus
okay.
1
So we can be talking.
L minus 3x L minus 3x plus y
If that means you have to come, you have to see. You have to be talking. Yeah? It's fine. Okay. No wala. Alright. So plus Z on the L and also minus 1 on the L. That's all of our L factors. Then we have T. So here we're having T raised to the power of minus Y. Then we have T raised to the power of minus 2. So just add minus 2. Very good. So what do we do here now?
by 1 equals to
I think we're set. So pi is a dimensionless constant, meaning that this is M0, L0, and T0. So what's the idea of pi in Buckingham theorem? The idea is we want to bring out multiple number of dimensionless quantities. And we call those quantities numbers, dimensionless numbers. So how do we know the number of dimensionless pi terms that will be present in a given number of quantities? It's just to obtain the number of variables that are available and then check out the total number of dimensionless fundamental quantities there. In this case, we only have M, L, and T, and that's all dimensionals, and that's why we have here as 3. So our pi, number of pi terms will be equal to pi equals to n minus m, that gives us 6 minus 3. So we know that we are supposed to derive 3 dimensionless numbers from these arrangements.
yes.
Right here. So I think from there, what we will do now, let's express this here to make the comparison easy, right?
Okay, so having for m,
So for m, yeah.
we have m0 equals to mx plus 1. So x is equal minus 1.
So x is equal to minus 1. Yep.
So for L, we have L0, L minus 3x plus y plus z. And our x is minus 1. So we are having 0 equals to minus 3 open bracket minus 1 plus y plus z. That's plus 3. That's 3
Okay.
That's 3 plus y plus z.
That's
Minus
3
1
plus y plus
plus z
z.
minus 1.
Okay.
So what?
Let it y plus z. I think this gives us 2, right?
Okay. Yeah, y plus z that's 2. So y plus z equals to minus 2. So for t, we have t raised to power 0, t equals to t minus y minus 2. So we're having 0 equals to minus y minus 2. So y is equals to minus 2. So we're going to repeat it into equation 2 to get our z. So our z is y equals to minus 2. So another one.
Okay, sorry. I'm putting it into here.
Yes, so we're having minus 2 plus z equals to minus 2. So we're having z equals to minus 2 plus 2, which is equals to 0.
No, again. As you meant 2 minus 2, okay?
Yeah.
So therefore we can express our pi 1 as, we can express our pi 1 now as what?
My
As
one is density. Density raised to power what are x?
X was
Density
what?
raised to power minus 1. B raised to power minus 2. And D raised to power 0.
then lastly we add the quantity dot
Change the P.
together. So what do we now have on there?
But that one can be like
No. Pi 1
so pi is equals to 1 over density. 1 over change the P over density squared. So power pi 2.
so what's the next thing?
So I should look for pi 2.
So pi 2 here.
So at pi 2 we can pick viscosity, velocity, and pressure. Viscosity, velocity, and pressure. Viscosity, velocity, and pressure. Okay, so we're going to be having pi 2 equals to dimensionless number constant height. Pi 2 equals to dimensionless.
Sorry. Okay. I'm then out the noise outside.
Pi 2 equals to dimensionless constant. By using velocity, viscosity, and pressure. So we're having dimensionless constants. K, open bracket. K open
Dimensionless constant what?
K.
Having f the function of those three repeating.
Viscosity, velocity, and also use the same exact.
Yes, exact.
So anything you pick from the beginning.
Yeah, to use. It's only that outside when you change.
Okay, so let's consider using viscosity now.
So we haven't used viscosity, right?
Yeah. So we're having pi 2 as pi 2 as so our pi 2 is we already got what our density was before. Should we just do that?
I'm coming. So here we have what?
Density raised to power minus 1.
So we
Density
have
raised to power minus 1.
density.
Okay, no, I think it's my it will change. NL minus 3 raised to power of x. LT minus 2 raised to power of y.
Minus 1.
X minus 3 minus 1 raised to power of y. Then L raised to power of z. Dot NL minus 1. T minus 1. So our pi
Hold on.
will be N0, L0, 0, T 0 equals to fx L minus bx Ly T minus y Lz dot L minus 1 T minus 1. So for n, we're having for n mx plus 1 L minus 3x plus y plus z minus 1, then t minus y minus 1, t minus y minus 1. So we're now having for n, we have so for n, we're having
I'm coming. So I'm coming. What do we have now?
okay, so for n, we have n raised to the power of 0, n raised to the power of 0
I'm coming. 0.
equals to mx plus 1, making us have x at minus 1. Then for your L raised to the power of 0
Wait, I'm coming.
minus dx plus y plus z that's equals to L raised to the power of 0. So we're now having minus 3x plus y plus z minus 1 equals to 0. Minus 3x plus y
Is that what you're saying? What did you call that? Okay, like so open that one. Sorry. So minus 1.
having minus y equals minus 1. No, minus y equals to plus 1. That's y equals to minus 1. So for n raised to the power, so minus 1 plus minus 1. Now why is minus 1? So it's supposed to be minus 3 open bracket minus 1 plus minus 1, which we have minus 1. Remember, you got minus 1.
I'm coming.
Minus 3 open bracket minus 1 plus minus 1.
Plus minus 1.
Yes.
Plus
minus 1 plus z minus 1.
Because what?
Plus z minus 1.
Is that not that
You were writing it right. But you already wrote plus minus 1. You're writing it again.
It's what you're calling it. It's not right. Am I getting this one?
Doing that, doing one of that plus minus. So what you have is minus 3 open bracket minus 1 minus
Wait,
one.
let's write it. So minus 3 into bracket
Minus 1, then minus
plus
1.
minus 1. Then
Plus
z is
z.
what?
We are looking for z, then minus 1 equals 0. Then minus 2, that's 3 minus 1 minus 1. That's 2, 1, that's the z equals to minus 1. So in the equation, our pi is equals to pi 2 is equals to our pi 2 is
equals to density raised to the power minus 1, b raised to the power minus 1, z raised to the power minus 1. Okay, so we're having dots, there will be dots viscosity. Yeah, viscosity. So then we're having pi 2 equals to 1 all over density dz.
Which one?
D. Yeah, D. 1 all over density, mu all over density dt, exactly. So that's it. So for our pi 3, so for our pi 3, so for pi 3,
Wait. I want to ask you something. Did you tell me last time I was going to go and fetch me? No. It's important. Talk. Guinness will not talk.
for pi 3, yeah. Density dots. Density dots.
I'm coming. Yeah, call.
Pi 3 equals density dt.
What is it?
Dot L. Density V D dot L, yes. Writing L dot L. Normal L. Dot L na hence. So density, that's pi L open bracket, L minus 3 raised to the power of x, L minus 1 raised to the power of y, L raised to the power of z, plus L. So 5 that's F3 nx L minus 3x Ly c minus y Lz plus L. So that's 5 equals to mx L minus 3x plus y plus z plus 1 plus y L minus 3x plus y plus z plus 1 0 minus 5. So n raised to the power of 0, L raised to the power of 0. Just the n raised to the power of 0, L raised to the power of 0. N raised to the power of 0, L raised to the power of 0, C raised to the power of 0 equals to n raised to the power of s, L minus 3x plus y plus z plus 1, c minus y. So for n, we have n raised to the power of 0 equals to
How should you?
equals to s. So s equals to 0. S equals to 0.
Is this it?
N raised to the power of 0 equals to n raised to the power of 0 equals to nx. No, cancel that one in root 4. Cancel that in root 4.
This one?
Everything.
Is that not okay?
So n raised to the power of 0 equals to n raised to the power of x. That's 0 equals to x here. So for L, L raised to the power of 0 equals to L minus 3x plus y plus z plus 1. So 0 equals to minus 3x plus y plus z plus 1. So 0 equals to minus 3, 0 plus y plus z plus 1 plus y plus z plus 1. So 0 equals to 0 plus y plus z plus 1. That's 0 equals to y plus z plus 1. Yeah. Okay, so for your t raised to the power of 0. T raised to the power of 0 is equal to t minus y. So y is literally equals to 0. So z is equals to minus 1 here. So our pi 3 equals to density raised to the power of 0, density raised to the power of 0, b raised to the power of 0, and d raised to the power of minus 1 dot L.
This is about my one dot L.
Now, we are already doing on that.
As now.
The L at the back now.
Yes, is it not L this one? So that is L like this now.
Yes.
So that's all.
So pi 3 equals to density raised to the power of 0, b raised to the power of 0, z raised to the power of minus, d raised to the power of minus 1 dot L. So pi 3 is equals to 1 over t, L over t. So that's it.
I'm fine. I'm not going. I'm still in frame. I'm still. What did you do? Huh? Don't worry, I'm telling you. Listen.
Okay, so are we solving more questions? Are we solving more questions now?
I'm still working on solving more questions.
Okay.
No problem. I'm going to vectors. I'm going to vectors now.
We're going to.
Vectors. Huh? Impossible.
So vectors.
Relax.
Vectors.
So, we're going into vectors now. Solving questions like that as well. We're setting on dots, products, and cross, products. Set on dot products and cross products. What are you doing? Don't do that, don't worry. I'm telling you. That's it.
Vectors.
So we have this. Giving okay. Come and sit down with me so I can use it. Bring the chair. So I can see something. Let me call it. No, I'm fine. You went down long. I don't want you, don't worry. minus okay. Determine. Let's see.
So determine A dot B.
So.
Determine A dot B.
Okay.
Then the angle between vectors. Then question 2.
Oh no, let me do this one first.
Question 2.
Still on that.
Yes, let's write answer. So find the work done when the points of S 12, minus 4.8 meters.
Let's just do one first. That will not be clear. Let's just do one first. So from here now, these are the vectors. We have the vector A written out here, vector B written out here. So therefore, we want to establish a dot product between A and B. So to get a dot vector, we multiply each of the vectors. So 3 times 5, we have 15. So we have 15 minus 2 minus 8, right? And that will be equal to something. That will be equal to 15 minus 2 is how many? 13. 13 minus 8. 5. So that means our dot product A dot B is equal to what? 5. So how about we get the modulus of the vector? The modulus of the vector, what does it give us? So we have what? Modulus of A is equal to what? Square root of what? 3 squared minus 2 squared plus 4 squared. Then B is equal to what? 9 what? No, B is 5. 5 squared. Yes, 5 squared. Plus 1. You can see that plus 1. Plus 1 squared. One point 4.58, have you?
Yes.
Then which other one do we have? 4.69. Then which one do we have again? I think these are the 2 vectors that we're having. So what else? So we are having, now that we have the modulus, they said we should find the angles between the vectors, Abi. Yes. Now we have determined A dot B. A dot B is what? Is 5. Right? Yes. So therefore, that means we are having, to get the angles between the vectors, we are having what? A dot B, which is 5, equals to what? Modulus of A, which is 4.58, times what? 4.69 cos theta equals to, multiply this, what does it equal to? Multiply it.
21.48.
Thank you, that's cos theta divided by what? 21.48 over 21.48, right? So what do you now have? Divide it. I didn't get you. 0.23. The cos inverse of 0.23 is equal to what?
6.70.
Okay, so what's the next? What's the next? Next question. So we have it here. All right. Now in the next one now is an application of the dot product. It said find the work done when a force. So we are like find the work done when a force. Force is find the work done when the force and the work done when the force F is equal to what? 12 comma minus 4 comma 8 moves an object through S 5, 2, minus 1 meters. So here now, this one is another problem on its own. So this is your force in vector form, and this is your what? Displacement in vector form, have you?
Yes.
Very good. Now, but finding the work done, now work done is equal to what? Force dot distance, right?
Yes.
And even if you say it acts in the direction of the what? Of the force. True or false? So from there, we have what? You can get our A dot S. This I just put it there so you can know it exists. So W is now equals to, this is our F, 12, comma, minus 4, comma, 8. This is a 3-dimensional vector, right? Open, we have what? 5, 2, comma, 1. So 12 times 5 is what? 60. Minus 4 times 2 is what? Minus 8. Then we have minus what? Minus 8. True or false? So, next question. From there you can solve it, right? So that gives you what? Automatically. That gives you 44, yeah. 44 what? 44 joules. 44 joules. All right. Now the next question here, they are talking about show whether the vectors A and B, the road vectors out are perpendicular. So, they gave us these vectors, and they want to say, the question says show, let me write it here, show whether the vectors, okay, instead of there, right? Instead of that side, I can put it. Show whether the vectors are perpendicular So what do we now have now? Vector A is equal to what? 4, comma. Comma 0. So from here now, what do we now have? So now, it's dot product that we can use to confirm. So under what condition is it going to be perpendicular? When the dot product is equal to what? When the angle of the dot product is equal to what? 90, Abby? Because sin, cos 90 is what? 1. Okay. So we know that when the dot product of the vector angle is equal to what? Listen, you have vector A vector B cos theta to be A dot B, Abi? Yes. And then you have vector that's equals to, and we also have another condition where we say vector A cross B to be equal to vector A B sin what? Sin theta. True or false? So what are we now going to be expecting? We'll be expecting that what? Chief? I don't know. I agree to you, boss. We'll be expecting that what now? We'll be expecting that if it were to be this one, right? It were to be this vector turns into 0 here. When what is happening? When theta is what? When theta is 0, Abby, sin 0 gives you 0, right? So when it is 0 here, it means that what? That these vectors here are what? Why? Because the angle is 0. Angle between 1 and use your mic now. It's an interaction. It's an interaction. Use your mic. Angle to. Okay. That's also a possibility if you want to do that. But let's see. So we have vector what now? It's equal to. We have 4. Let's just put it in unit vector. So 4i minus 2j plus 6k. Then b, vector b here you have what? 3i plus 6j. Then what? Plus 0k. So let's quickly check up the angle. So to check the angle, we can just say a dot. I'm coming. We can get the a dot b quickly. That will be how many? 12 minus 12 plus 0. And that gives us what? 0. Please, because what is going to give us 0? Is it cos 90? Yes, cos 90 gives us 0. Yes. So it means that these vectors are what? Are perpendicular. So because the condition of perpendicularity is when your a dot b is equal to what? 0. I guess now when a dot b gives you 0, then vector a and vector B perpendicular. All right, so that's for that. What's next? What's next? So that's all under that aspect. So good. Next question, we are looking at, we have a vector question here. Because of our time, let's just really do a cross vector question. Cross product question. So we have this vector that said, find the area of the parallelogram. Find the area of the parallelogram. No time. Find the cross product. Look at this problem. Find the cross product of the vectors. What are the vectors? 2, 3, minus 1, and what? 1, comma, minus 2, comma, 4. So yes, solution. Solution. What do we have? If what give they asked, they said, find the cross product of this. That you are going to be using this. This is what they want us to get. If this vector A and vector B, we want to get what? P is equal to what? Oh yeah, so what do we have? Plus minus plus. From there, what do we do? We pick one side close and this side close, right?
Yes.
So what would that be giving us? Plus I open bracket what? Minus 2. Minus J. 8 plus 1.
Plus K.
Plus K.
Minus 4.
Minus 4.
Minus 3.
Minus 3. Plus I open bracket 10. Minus J. 9.
Plus K. Minus
Plus K.
minus 7. Minus 7K.
So we have gotten this. Then we want to get it in a vector, in a scalar form. That means we don't want it to be I, J, and K kind of thing. What we will do? 10,
10,
We're doing something like this.
Is it the plus?
Yes, 10 plus.
Minus 9 squared. Minus open plus open brackets minus 7 squared.
So what do we have now? 100 plus 81 plus 49 is what?
15.165. Like everything. Should I give you in short form?
In what?
Give you 230.
230. Which gives us what?
15.165.
15 point what?
0.16.
16 is what?
Estimated.
Okay, very good. Very good. Okay, we'll go for further vector questions now. So let's just look at one way they used to apply this cross product. They said find the torque produced by. They said find the torque produced by. Find the torque produced by R vector equals to 2, comma, minus 1, comma, 3. And F five, comma, so what do we have? Good. So what am I having now? So I'm having FR is equal to, we want to look at the cross product because torque is a cross kind of product stuff. So I did I, J, K, 2, 3.
5, 4, minus 2.
So we're having, yeah? Oh, sorry.
Plus I, bracket.
So
2 minus 12.
2 minus 12,
Minus J, bracket, minus 4, minus 15.
minus 4. Then we have plus K here.
Bracket, minus 4,
Then we have 2 times 4.
that is 8 plus 5.
So what do we have here?
I bracket, minus 10. That is
Minus 19
plus 19.
plus 19J. What else do we now have?
Plus 13.
Plus 13K.
K.
So what do we now have now? So this is the vector. Even if you want to get it in scalar form, what will you do? You find the modulus. That's if you want to do that. And find the modulus means that we're doing minus 10 square plus 19 square
plus 13 square.
$19 square. 19 square.
90 square is 361.
361, okay.
Yes. Plus 169.
Plus 169. So what do we now have?
The final answer is 20.34.
That's final answer everything together.
20.74.
20 points what? 74. Newton what?
Meter.
Newton meter, okay. Sharp. Okay. So we're going to kinematics. We're going to kinematics. Yeah, like we're solving questions, topic by topic. Kinematics. No, we've done them. Kinematics. Okay. So we're starting with projectile, horizontal projectile. A ball is projected horizontally from the top of a 45-meter cliff. So let's imagine that there's a cliff here. The ball is projected from the top of a 45-meter cliff. 45 meters cliff. 45 meters cliff. This one. 45-meter cliff. That's what you can. 5 minutes. 5 minutes. Sorry. 5 what? Yeah. So the question says a ball is projected horizontally from the top of a 45 meters cliff, Abi. From the top of a 45-meter cliff with a speed of 20 meters per second. So what do you now have? The ball is projected from the top. So the height of the building is 45 meters. Determine the time taken to hit the ground. Determine the time taken to hit the ground. So whenever you are given the projectile question like this, where you have to, maybe this is a horizontal projectile kind of situation, and you are told to calculate time taken to get to a particular point, right? You have to be able to check where that point is and reference that point. And this one I'm talking about getting to here, which is actually the end of this flight, right? So the best thing you can just do is to take advantage of any of the positional vectors. Are you there now? Then use those positional vectors as well to do what you want to do. So for instance, I can take this 45 degree. I'll take this 45 degree. I'm sorry, this 45 meters as height, right? And then I know that normally, if I was going to be studying the motion from the horizontal perspective, I would have had this horizontal positional vector, right? So we had 45, or we just had x. So if I want to get the time, h is equals to half gt squared. You understand? So we are going to be having what? We are going to be having what? So here we are having h is equals to 1/2 times 10 times t squared. And this h is what? 45. Do you get that? So what do we have there? 90 is equals to 10t squared. So divide both sides by 10. T squared is equals to 9, which makes t squared of 9, which is equal to 3 seconds. 3 seconds. Do you get that? So what else? What did? What's the next?
Next question.
Then they said horizontal distance traveled. What's the horizontal distance traveled? S is equal to what? UT, which is equal to what? What's our U?
20 times.
Our U is 20, right?
Yes.
The body was projected with a velocity of 20 meters per what? Second. So here we have 20 times 3, which is equal to what? 60 meters. Are we together here now? That's 60 meters. So the next one, we have magnitude of the vector just before impact. Magnitude of the vector just before impact. Magnitude of the vector just before impact. So that means at this point here, right? So this is where you get to understand something. Horizontal component of velocity in a projectile motion is constant all through. It's constant all through. So even when it got to the end, it still retained this value of horizontal. Its Vx is still remaining Ux, which is this 20 here. But the vertical do change. So to get the answer, we need to know what the vertical component of velocity will be. And it's very, very simple to get. So we just say Vy is equals to Uy, because the initial component of velocity is usually what? The initial component of vertical velocity, that is Uy, is usually 0. So mine plus gt. We already know the time is 3. So that means the final velocity of this body is 0 plus 10t. That is 10 times 3. Thank you very much. So Vy is equal to what? 30 meters per second. You get? So from there now, what do we have? Vy. So we have, that's the velocity with which you impact the ground will not be what? Yes, it's vector. Yes, when they tell you find what velocity does it strike the ground, it's the resultant velocity. So that V is now equals to what? Square root of Vx square. So we're having V is equals to Alright, plus what?
30 squared.
Is it 30 twice?
One is 20, one is 30.
Who is the 20? So
The final answer is
V is equals to
36.
everything is what?
36.06
36.
meter per second.
Yes. So that's it. So what do I call it? 36.06. So we now have this. Another thing they asked you for is the angle with which it struck the ground. I think they would have asked it. They said direction of the velocity just before impact. Direction of the velocity just before impact. For that one, now what are you going to be having?
Theta is equal to tan inverse.
Tan inverse what?
Vy over px.
Vy over what?
Px.
Vx. So tan theta is now equals what?
Tan inverse of
Of what?
30 over 20
30
over 20.
over 20. So what do we now have? Theta is equals to what? Tan inverse of what? 1.5.
Amp is equal to 6.3 degrees.
So theta now is equals to 56
31 degrees.
or 31 degree. So that's it. That's it. That's all on that side. Wait.
Next
Yeah, where is it?
Next question.
A stone leaves a table 1.5 meters high at what? 6 meters per what? Second. Where's the duster? Yes. Okay. Eh? What is it? Yes. Are you following what I'm saying here? So what are we doing now? What are we doing here? Somebody talk to me. Resultant. So we are doing V is equal to square root of what? Vy square plus what? So Vy is now equal to what? 5.5 square plus what? Plus 6. 6 on the dot, Abby?
Yes.
Square. What's the answer?
8.14.
8 point what?
14.
Very good. Meters per second. Very good. We move. We are still on projectile. Let's touch some level of vertical projectile. Okay. Yes. Let's go. Okay. Now this one says a stone is thrown vertically where? Upwards. Vertically where? Upwards. Are you following me now? The one we've been doing is when you are thrown horizontally. Are you getting me? We have been doing one of thrown horizontally. This one now we are throwing is what? Vertically. So let's see what that will look like. All right, let's go. Let's get into it. A stone is thrown vertically downward from 100 meters building with an initial speed of 10 meters per second. Now, this is it. First thing first you want to do is you want to be imaginative. They said this stone was thrown vertically upwards, right? From a 100-meter building. So what's the height of this building, please? From here to here is 100 meters. Do you see that now? They said a stone is thrown vertically upwards. That means straight up. I get what I'm saying now? From a 100-meter building. That means they threw this thing from a height above the ground that was what? How many meters above the ground? 100. Now, let me dash you this information. Anytime such a thing is given to you as a person, understand that you are going to be studying that motion like a graph book. Like a what book? Graph book. I will tell myself the region of takeoff will be my 0 mark. Will be my what mark? 0 mark. That will be my 0 mark. Will be my 0 mark. Now, they said with an initial speed of 10 meters per second. So this bro was thrown up like this. And obviously, when it's coming down, it will fall down to the way? Ground. That's the kind of motion they gave us in this question. Now, my question is this. What was the initial velocity of this speed? Of this projectile? U equals to what? They said it was what? 10 meters per second. Thank you very much. 10 meters per second. Very good. Very good. Very good. Now, first question, they said, find time to reach the ground. Time to reach the what? Ground. Now, this is where students make this error and physics becomes too much of a task. Some of you want to break the motion into two and tell yourself, let me first look to move from here to maximum height, then from maximum height to the floor. If you can use what I call the computational method, enter the positions in their sign form and see what magic happens. Everything just solves itself by itself. You will even see by yourself that this thing has solved itself. Let me show you what I mean. I will use only one equation to solve this. I won't break it down. I should use that instead. Okay. So this thing has given issues. So this is making this noise. Oh. Okay. All right. So. Okay. So the vector came from here, went up. I'm still hearing that it's not coming out well now. Hello. I think we have the second spell, in case it's the speaker. Reach out to any member of the technical team. Tell them to bring the second speaker. All right, so let's continue. Please, that will be solved in a short period of time. I would just rather... Where is it? Here, please. All right. Okay. All right, it's getting better now. I think it's not this. Yeah, that's good. This. All right. Thank you so much. Okay, it's coming back. Okay, so should I just leave this first? Let me just use my voice for a while. Please just manage and bear with me. It will come back in a short period of time. Okay, so the projectile will move up, bend, and take a turn where? Down to the ground. Please follow me carefully. When it got to this ground, I told you that there are many ways you can study that motion. Instead of decomposing the parts, it's better you compute it. Now, the question you ask yourself is, in vector, following the instruction I told you, in vector now, if you want to look at this like a vector stuff, like a graph, this point, you said is our takeoff point, is our what mark? 0. That means if this floor, this ground, is 100 meters, that means the exact end is how many meters? What would I call that exact end, the floor? Will I call it 100 or minus 100 for the fact that it's going down? That means this place on the graph is negative 100. No, welcome, okay. This one is okay, Abby. Reserve. So can I go back on this? Okay, is it working? Not working. I have not on it. Okay, I have not plugged it. All right, that's perfect. That's it. Okay. Okay. Now look at what I'm saying. This place is about minus 100, Abby. You will see that to get that answer, we never even need to have gotten the maximum height anything. We will boycott it. The equation will solve itself. Now look at it. I am moving away from a point called what? My projectile started from a point called what? A point where my y was what? My y1 was what? No, the takeoff point. Takeoff point. 0. I told you your point of takeoff is the 0 mark. So if you throw up, you are attaining the positive kind of positionalism, Abi. If you are going down, what are you attaining? Negative. So you took off from a point 0 and ended at a point what? Minus 100. The stone, not you. The stone took off at a point where? 0. Ended at a point where? Minus 100. Look at what will happen now in grand style. I'll be having my 0 here. Initial takeoff. Abi?
Yes, sir.
That means I will call this 0 my y. You know it's y. The motion is along y, so we're not calling it x. I will call this 1, y1. My y1 is what? 0. But what's my yf? The final position I ended up in? Minus 100. So I'll call it minus 100. Minus 100 because it's going down. Now, guess what? All we just need to do now, we know the initial velocity is what? Initial velocity of y is what? 10 meters per what? That was what the trim up it from that is 0 position. Very good. Now, another brother that we know is g. What's the value of g forever and ever? 10 meters per second. Is it going to be plus 10 or minus 10, somebody? Is it plus 10 or minus 10? Minus 10. Because the guy is starting from what? is starting from his initial movement started against gravity. Don't bend, don't pretend, don't try to judge, because some of us now judge that like I will use plus 10 because he spend more time going. It is your reference frame is your starting point. When he was taking off, it took off with what? Minus g. So good. This can solve. This can solve. What can we use to solve this? Do you remember that formula that this we call H is equals to UT plus, okay, we have, let me just write out all the equation you have. Plus or minus what? 1/2 GT squared. You know that equation, Abi? Okay, let's keep that on one side though. You also know the one that they used to say V squared, I'm coming, is equal to what? U squared plus or minus what? 2GH. You remember that one, Abi?
Yes.
Okay. Now, I can use this to know my final velocity. Do you know what this will give me? It's giving me the velocity here. Direct. Maybe they told you find the velocity used and strike the ground. No need of breaking it down. It's one equation. You have given me that one also. We also have that other one that you say S is equal to what? V plus U over 2 times T. So now, we're dealing with H. Now, the best thing that you can just do, I get it now, since they did not give you time, any of those things, you can just, first of all, use an equation that gives you the value of velocity on this place. I get what I'm saying now? Gives you the value of your final velocity. And that's this brother here. Somebody help me, what will I write? V square is now equal to, what are U square? 10 square. Am I using plus or minus? Minus. What am I having here? 2 times 10 times our H. I told you I will work with it, Abi. Computational. Where's our takeoff point? Where's our final position? Final position is minus. Initial position is what? Plus 0. Do you understand what I'm saying now? So we're having minus 100 minus 0. You understand? So let's solve. Vy squared is now equal to what? 100 minus times this minus here now written. Plus. Somebody help me. 2 times 10 now written. 20 times 100 is what? I can't hear you. 2,000. Altogether, our Vy squared is equal to what? 2,100. Vy is now going to be equal to what? Square root 2,100. What's our Vy?
45.83.
45 point what?
83.
45.83 meters per second. Do you see how we got the final velocity without having to go to maximum height and say, oh, maximum height 0 first, then now calculate from 0 to. You don't even need. This is a computational system. Let's still use this computational system again to find the. You can use to get anything you want to get. You can use and get the total height of flight, time of every. Let's get the time of flight. Let's get the time of flight. What will we do? Just look for an equation that has time of flight and let's use. Should we use this one? This one will take us to quadratic. Let's use that one that V is equals to U plus GT, Abi. But now that we're going up, we use what? Minus GT. What's our V? 45.83 equals to what? 10. Are you following what I'm saying now? Then what do you now have here?
Minus 10 times.
Minus 10t. Are we getting what I'm saying here? Now let me teach you something about the computation. This velocity, we are agreeing that this velocity is a positive velocity. This 10 is a positive velocity, Abi. Nobody's answering.
Yes.
Why? Because its motion is upward, Abi. But this 45 that we got, the final velocity, is it a positive velocity? Because it was going down. It was going down till it struck the ground. Like it is actually a negative velocity. That's why we're going to put negative in this place. Because it's a negative velocity. Carry this one here and carry this one here. What do you have? 10c.
Sorry.
Yes.
So which minus is the final answer of that you are?
I didn't hear you.
Which minus is the final answer of that?
No, now. Like, you know that this answer now is telling us that the velocity, we are not giving information about direction. My velocity was 45. But you know that you are the person that wrote it. If you want to add direction, then you know it is downwards. The examiner self knows that it's downward because the question shows it. Do you understand? But when I want to use that velocity and solve, it means that when I know that I want to use this velocity and solve another question. No, I have to obey the law of vector. That velocity was going where? Down. It's a negative velocity. So you put it there. When you put it there, what do you have now? Tell me. 10t, 10 plus 45. Are we together here now?
Yes.
Okay. So we are now having
10 is equals to 5.83.
so divide both sides by 10, have you?
5.58.
5 point what?
583.
Was there any stress? No. 5.583 what? Seconds. That's the time. That's the time. Very simple. Very simple. Now, straight up. No having to break. You didn't break anything. It's just straight velocity and that's all. Let's see what they ask again. Speed at impact. We've gotten it. Come and see it. Second question. Speed at impact. What is the speed at impact? That is that final velocity. You know that this one is not a two-dimensional motion now. It's straight up, straight down. No x components. They're just walking straight up, straight down. That's all. Very simple. Let's bring out one question like that. I want us to see ourselves, harness this information, utilize it here and now as I'm solving it. In fact, be ahead of me. Let me be at your back as I'm solving. Make sure you fill it for me so that I can tell you how far I will reach. I would like that. Let's go. Before the end of this class, I would have done that. Now, before that time, before then, before I'll give you any class work to do, how many of you have done what we call angular projectile? Where they will tell you that the projectile and the body to maybe at an angle of 45 to the. You have done this kind of projectile now. What are the three things they should ask you in that projectile?
Time of light.
Time of light, maximum height, and range. Then the moment they tell you, calculate the final velocity at a point 2 seconds above the ground or 1 second before it reaches the ground. That place people should leave it for the examiner. Like, it used to be like extra 2. The way they are laughing. It looks like it is what you do. Now, it's a very, very simple approach too. Very, very simple approach. Very, very, very simple approach. Now, what are we going to do? Coming? Okay. This is what I mean. This is what I mean. Okay. Let's write. A projectile is fired. Okay. A projectile is fired with a speed 40 meters per second at an angle of 30. Find the time of flight, the maximum height, and the horizontal range. Those ones are the three that we are used to. Now, number D, part of that question, part D, find the resultant velocity. Find the resultant velocity 1 second before it completes its projectile. You know, that means before it got to the floor again, 1 second before that time. That's what we are asking for. Is it too much to ask for? It's too much to ask for. It's too simple. Let me say it's very simple. Now, everybody, let's draw the diagram. There's a vector diagram for that. We have what? True or false? Okay. Okay. So we know the object passed through this part. But one of the most important things we want to identify here is the what? Is the initial velocity it uses to go. What's that initial velocity, everybody?
40 meters per second.
I can't hear you.
40 meters per second.
40 meters per second. Are we together here now? Then, if the angle was given to us to the rear. That means it is. See, let me tell you something you should know. If they write 30 degree, 40 degree, anything from 0 to 89, without putting all those to the, that means it is coming from the way, from the east. It's coming from. It's going to land on the horizontal side. Once it's not going to be like that, that's when they will start giving you all this correctional information like not something degree. So since it's also 30, that means you're doing it 30 to the way, horizontal. I get what I'm saying here.
Yes.
So good. Now this 30 to the way, horizontal. How do we now project? How do we resolve the vector? This one is going to be our vertical component of velocity, which we label as what? 40 cos 30. This one will now be what? 40 sine 30. Are we together here now? Please take note of this. Take note of all this. Very, very important. Take note of it. Okay. From here now, if you want to answer the time of flight, what do you do? If you want to answer the time of flight, what do you do? Oh yeah, what's the formula for time of flight? Time of flight is the time from the place it was projected to where it lands on the projectile again. And the formula is what? 2u sine theta over g. Please, everybody use that formula. 2u sine theta over what? G. 2u sine theta over what? G. That gives you your what? Time of flight. When you want to get maximum height, what formula are we using? U equals to what? U squared sine squared theta over 2g. And then range gives you what? U squared sine 2 theta over g. Oh yeah, that's it. Let's get on with it. Let's get on with it. Let's get on with it. What does it give us? For time of flight, what did you get? So for time of flight, I'm expecting
4 seconds.
how many?
4 seconds.
So t is equals to 2 times 40 sine 30 over 10. T is now equals to what?
Like 10 times
10 cancel this one. We have 8.
8 times
8 sine 0.5 is what? 4. Abby?
Yes,
4. Very good. 4 seconds. Are we together here now? Hello, are we together here now? What about the height of flight? What's going to be your height of flight? That is your maximum height. Your maximum height, I mean.
yes.
What's it going to be?
40 square.
40 square.
Sine square.
Sine square what?
30.
30 divided by what?
2 times 10, that is 20.
Times 10, 20. So we're having what now? We're having what now? 1,600 sine what? Sine 30 square. Do we get that now? Okay. So what does it give us? So from here now, I need to give me it's over 20, year 0, year 0, year 1, And here we're having 80. Everything together is what?
20 meters.
20 meters. What's the last one that we need?
Range.
Horizontal range. How do we get the range? Range. So what is it?
U squared sine theta over.
What was U, please? 40 sine 2 times what? 30
Over 10.
over 10 sine 60. 4 sine 60, that's the answer. So what's the answer? 4 sine 60. 4 sine 60, that's what?
Final answer.
Yes, what's the answer?
138.56.
138.56 meters. Okay. Now, listen up. Now, we said that we want to calculate the flight, the what? What do you say we want to calculate? The next part. One second. Before completing the projectile now. So, everybody listen up. This is where it gets interesting. It's as good as saying that we want to reference some points here, maybe somewhere around here. Want to say, maybe imagine it was from here to this down that was the remaining 1 second. We now want to know what velocity was at this point, because they said find the component of velocity. It's very simple. You are not doing any maximum height thing and all those plenty things. Computational process. This is secret as a JUPEP student. If you don't follow this method, you are stressing yourself. Now, see what I'm going to tell you to do. One or two things. The first one is to start from this place and run your projectile, obeying the rules from here to here. Knowing that if the total time of flight was 4, that means the new total time of flight you'll be using should be how many? 3. Right? Should not be 3. With the same, what they call it, with the same initial component of velocity. You see what? I see now. From where? From here, like this is the part that is 3. Yes. So this is the part that was remaining for him to complete the motion. So they said that we should calculate the speed just at that point. I get you now. So what am I going to do? I'm going to tell myself, what was the coordinate of projectile at this point here? In terms of position, was it not 0 for both y and x? Both y and x started from here as 0, 0. Now check something though. What did I tell you about horizontal projectile, everybody? In any projectile, angular, anything, horizontal component of velocity is constant all through. Is what? Is constant all through. That means, what was the horizontal component of velocity as at the beginning? 40 cos 60. That means even as at this level, it was still what? I tell you, that was it. It was still 40 cos 30. Where we are going to have problem is in where? Knowing what the Vy is at that point. Vy. And I promise you, it's not even a problem. Just solve it as if you are solving the normal y vertical something. And it will give you the answer. Solve it like you are solving the normal y vertical motion. It will give you the answer. Now look at this. So look at this, somebody. Look at this. If I'm solving it that way, it means that my initial component of y will be there. And I'll just say, okay, I want to use Vy equals to Uy minus. Why am I using minus? Because the projectile is starting upward, abi? So minus GT. The question now is, what time are we using? Are we using the full time of flight or the time to get to that point? Time to get to that point, abi?
Yes.
Who can tell me what the time will be?
3.
Thank you very much. 3. Because the total time is 4. The time to get to that point will now be what? 3. So this place is going to be what now? 3. This place is going to be 3. And then we can find Vy. Vy is now equals to what is our horizontal component of velocity?
Zero.
At the beginning, no, it's not 0. If it's a horizontal projectile, it will be 0. But this one, it has. Look at where we resolve each of them initial components. What was the initial? It was 40, Abby?
Yes.
Very good. So we have 40 sine 30 minus G is what? 10 times, what is our T? What's our T? Yes, what's our T? 3. Very simple, though, very simple. This place now that we put this something like this, what are we supposed to be having? Theta, our theta is what? 30. What does it give us? Vy is equals to 40 sine 30 is what? Please be sure. 40 sine 30. You are saying different things. 40 sine 20, very good. Minus 10 times 3 is what? 30. What's our Vy like that? Minus 10 meters per second. If you had gotten a positive value, you should have been sure that you were wrong. Like if your answer was positive, you are supposed to be confident you have to cancel. Do you know why? Who can tell me why? Because if you look at the motion, that time was at the other side, where the component of vertical distance was already pointing where? In the downward direction. Do you understand what I'm saying? So automatically, okay, I'm changing now. So automatically, it means that what? It means that our, hold on first, it means that our Vy will be equals to 10. Our Vy will be equals to what? 10. So therefore, in this place here, physicist, hey God. In this place here, Vy is equal to what? Minus 10. How do we get minus 10? 20 minus 30. Minus is just telling you direction. If it was plus, it means it was going up. If it was minus, it means that it was in a period of time when it was what coming down. You can't get minus 10 in a place that is around here. All the vectors here are pointing upward for vertical. All the ones pointing down for verticals, they've already turned. They've taken their turn. They're already pointing down. That is how we know that the answer is supposed to be something that already what? Turned. So we now know the Vy. How do we get our final answer, everybody? V equals to what? Vy squared plus what? Vx squared. True or false? So we now have V equals to square root 10 squared plus. Have you resolved this one? What's the value? Thank you very much. 34.64 square. So what's that answer? V is now equal to what? Square root of what? 100 plus what? Woo! My family then. We for fight, we no come. So we now have what now? What is this here? Okay, I've squared everything, Abi. What's the answer? 36.0 meters per second. That's the answer. You can see how direct it is. Stop using decomposition. Go straight to computation. Go straight to what? Computation.
Ability.
Yeah. Technicals. The handlings, the fan, the gen, Windows, everything. Oh yeah. Question 5. Question 5. Angular projectile. That's another one again we want to touch. Now, I will give you guys a gift. Especially those of you that are advanced physics people. Yeah. You must have come through problems where they ask you to solve for projectiles on an inclined plane. There are ways to approach those kind of projectile. There are ways to approach those kind of projectile. Projectile on an inclined plane. So, what do we do? What do we do? So we're going to be having what? Projectile on an inclined plane. Imagine this was an inclined plane. And the plane is inclined at an angle of alpha. And then we probably have the projectile moving from a point at the start of the plane and it projects upwards like this. And it tells us, look for the time of flight. Without having to waste much time. Once you see this, maybe in our later series online, you will see the derivations. But in terms of formula, just remember that this projectile, if the angle to the projectile angle to the inclined plane is theta, once you apply a little twist of resolution to your gravity, you will get the answer. What's the normal time of flight? You guys, what's the normal time of flight? Normal time of flight is what? 2u sine theta over what? G. But if they told you that the thing was inclined at an angle, that it happened on an inclined plane at an angle of alpha, instead of writing ordinary G under here, you will remove that ordinary G and write what? I write G cos alpha. There are derivations to this, very long. If you want to learn the derivations online, you will see them. But just have it at the back of your mind that this is how you solve for it. If it said to be range, what's the formula for range? Sorry, maximum height. What's the formula for maximum height? H is equals to what? Sine squared theta over what? 2g. So here now H will now be equal to what? Yes? U square sine square theta over, remember, what are we adding? Cos theta. That means here will now be 2 cos alpha. That's it. 2g cos alpha. That's it. It's very, very simple. It's very, very simple. Just remember those formulas and you'll be good. Just remember these formulas and you'll be good. Sorry, the power will come on soon. All right. Let's move to the next aspect. Mr. Palime, let's open all the windows so that it's go. All right. We'll now move to dynamics. I didn't hear you. Okay, that was just that. It's not for the people. It's for advanced people. It's for you. It's in your maths. Yeah, yes, it's in your maths. The derivation is there. It's there. You can beg me later. Think about it. Okay. Okay, now we are going to dynamics. Now we are going to be touching few questions also in dynamics as a form of revision. Uh-oh. Okay, so we are having dynamics. Dynamics. All right. Dynamics is divided into a broad group of aspects, or broad group rather. What are they? You are going to be talking about the attitude and lift system as one. We will treat such today. We are going to be looking at what? Coefficient of restitution today. Yes, because that coefficient of restitution helps us to consolidate the idea of Newton's law of motion and rebound. Those two ideas, it helps us to bring them together. Good, and we're going to be utilizing them in this lecture. So, let's take for instance a pulley system or a lift system. A lift system. A lift system. Now, please watch. Watch. If this is a lift system, you have maybe, for example, you have a pulley, right? And the pulley now hung from here, came from here, and then you have this kind of stuff. Let's assume that this was M1 and this was M2. If M1, if M1 was greater than M2, who can tell me what will be the situation of things? How will this attitude rotate? It's not even perfectly vertical. Let me redraw it. Just like something bending to one side. Yes. When you look at this system, the question there is, how will this object rotate? How will they rotate? Given that M1 is greater than M2. Given that what? M1 is greater than M2. Will they rotate clockwise? Or they will rotate counterclockwise? How will the rotation be? This is clockwise. Will they rotate clockwise or counterclockwise? Okay, let me ask. M1 is heavier than this. Will M1 be going up or be coming down? Thank you very much. That means this is where downward motion will be. Then, what about this part here? It will be going up. It will be going up. Very, very simple. Now that we've known that, the question we now want to ask ourselves is this. For this object to be coming down, we know that there are two forces acting on it, Abi. The weight and the what? Tension. Weight and tension are both acting on it. Weight and tension are both acting on it. You have the weight. This one that's acting upward like this is the what? Tension in the string. Then the weight will be acting where? That is mg. How about this one here? That is going up. Why is it going up? It's because the tension was greater than the what? Weight. So the tension is this. The weight we want to act like this. But this one goes up because weight was what? Greater than. Sorry, because tension was greater than what? Weight. We can use that to solve. We can use that to solve. Now, M1 greater than M2. M1 greater than M2. That means I'm going to be having a system where what is happening? For M1 system, you are saying that the object is coming down. That means the weight is greater than the tension. Therefore, the resultant should be weight minus tension. Resultant velocity is mass times acceleration. Weight is mass times gravity minus t. Make t subject of formula. C will be equal to mg minus ma. You understand what we just did, Abi? Now, how about this one that is going up? We are done with this first part. Let's call it M1 because it was M1 we're using. Let's call it M1. M1, M1. Are we together here now? Good. For these other parts now, that the weight, that we said the tension is going up because the tension is greater than the weight, that means that one will be saying that what? For M2 system, For M2 system, what's happening to that one? The tension is greater than the what? So therefore, resultant will be what? Tension minus weight. The greater one first in both cases. Now, what that says is R, M, A, C minus M, G. Make T the subject of formula again. Who knows why we are using T as subject of formula? The tension. Because it's the same rope. It's the same rope that's holding this guy that's also holding this guy. These two bodies are, since I said tension are the same in the string, it means that what? This tension and this tension can be equated. We will now be having M1G minus M1A to be equals to M2A plus what? M2G. Are we together here? Now, you have a problem. What is your problem? Yeah. How? It's minus the idea, of course. Were you saying plus? I'm sorry for you, bro. Sorry. So sorry, bro. Oh yeah. What are you going to be having now? Let's confirm your eyesight. Tell us, what are we going to have? M1G. Carry everybody that have A to one side. Those that don't have A to another side. Oh yeah. All the A people one side, G people one side. That means I'm having M1G minus M2G. Then to the other side, we have what? M2A plus M1A. Let's write it. M2A plus M1A equals to M1G minus M2G. Factorize. If you factorize, what will you be having? A into bracket what? M2 plus M1, which is equals to what? If you factorize that one too, you get what? G, O bracket M1 minus M2. Divide both sides by M2 plus M1 by M2 plus M1. So our A is equals to what now? Open bracket M1 minus M2 all over what? M2 plus M1. That's it. Very simple. Very, very simple. The more composite system are already in our platform. If you want to see when they are inclined, maybe one of the pulleys, they're not standing like this regularly. One pulley is a slant, or the two are slant, or the multiple is the same. This, once you understand this, it's easy to understand that too. All right. Can I erase? This same principle happens in the lift. The same principle happens in the lift. In fact, if they give you a question that's to do with lift system, and they tell you to find your lift and maybe find your weight. Your weight in the body is the reaction. Your weight in the body is what? Is the reaction. So don't worry, just do the same thing you've been doing since. Just do the same thing you've been doing since. If the weight is moving upward, do the normal thing you do. That is, for it to move upward, that means reaction was greater than weight. That's what it will sound like, Abi. Don't worry. Just do like that. You see that is a very simple thing. Yeah?
Like if a situation, if like the mix, like maybe you use the wire connected to it and pot.
You have worked in that this thing before. You have done that kind of work before. Continue.
This situation.
Uh-huh.
Where and like lift points downward.
That's the thing holding the lift, the counterbalance has caught.
Yes. Yes.
Which lift did you enter? That there is only one rope to hold it. This thing. You have not talked true. Maybe it was your dream you happened to. Or you were on step and you drank. So you're falling, thought that you. So let's go. Let's go for a more. This is the first system you have. This is the first situation you have. Let's go for something else. Very good. Coefficient of restitution. Coefficient of restitution. Yes, coefficient of restitution is the biblical term. That is very, very hard to do. So, but here in physics, in an exam, they ask you define coefficient of restitution. The straight up thing you are telling them that this is what? A number or a parameter used in doing what? Measuring the degree of elasticity or inelasticity of a collision. So this comes from the concept of collision. It comes from the concept of collision. So collision can be defined as what, everybody? Someone, if you know what collision is, what does it mean? Impact, collision is what? Impact, contact between bodies. Impact, contact between bodies. That's it. Now that we know that that's what collision is, when two bodies collide, the scenario that happens are one of these scenarios. You can collide, find yourself sticking together, and let me just use the word, find yourself stuck together and moving with a common velocity like that. There's another collision where they collide and they separate, right? Maybe on the road, maybe there was an accident, you see them, they jam themselves and they separate. That one is elastic collision. When they jam themselves and they stick together, most times it's because maybe the one vehicle was larger than the other one. It's like the bigger one is just driving that one. That is inelastic collision. That's what? Inelastic collision. So let me make it clearer. In elastic collision, what do we experience? The two bodies do what? Separate after collision. But in inelastic collision, the two bodies do what? They stick together. And when you stick together, it means that people will not be behaving like one. That means you will not be moving with a single common velocity. So they stick together with common velocity v. That's it. Okay. But if you are looking at it from the microscopic perspective, that means the underlying formula description of that physical event you are seeing, you will tell yourself that what? That the elastic collision are those collisions in which both momentum and what? Kinetic energy is conserved. Momentum and kinetic energy are what? Conserved. But this other one here, momentum is conserved. Momentum is what? Conserved. But kinetic energy is lost. That's the scenario. Now, let's solve a question on that. Where you'll be needing coefficient of restitution. But before I will solve it, if a body is perfectly elastic, its coefficient of restitution will be 1. If a body is perfectly elastic, the coefficient of restitution will be what? 1. So let me write it here. Perfectly elastic, coefficient of restitution E is what? Is 1 of the person. But if the collision is perfectly inelastic, then E will be equal to what? 0. It is a very, very serious situation. Now, let's pick one question and solve on this. All right. Okay. This is the question. Let's this question again. Okay. They said a 1 kilogram ball moving at 12 meters per second collide head on. A 1 kilogram ball. A 1 kilogram ball. I don't know what's a 1 kilogram ball moving at 12 meters per second. All right, let's go. Let's write. A 1 Oh yeah, let's go. A 1 kilogram ball moving at 12 meters per second. 1 kilogram ball moving at 12 meters per second collide head on with a 2 kilogram ball moving in the opposite direction. Who can tell me how I will write that 1 kilogram ball on first? For the fact that they said they are moving in opposite direction, that means their velocity will be opposite. Which one is plus the round what? Minus. Do you get it now? So that means I'll be saying what? I'll be saying that what's the first ball? What's the first ball? 1 kilogram ball, Abi. Let's just say we have the ball 1, M1, U1. I guess me now, that's the information of the first ball, plus M2, U2. That is total collision before momentum. And the total momentum before collision is equal to the what? M1 V1 plus what? M2 V2 is equal to the total momentum after collision. Now let's put values inside respecting the rule and law of spatiality. a 1 kilogram ball moving at 12 meters per second collided on with a 2 kilogram ball moving in the opposite direction. So since they said 24 was moving in the opposite direction, that means it's 24 that will be the negative vector. It will be the one that will carry the minus. See what it is. Read it first. Thank you.
A 1 kilogram ball moving at 12 meters per second.
A 1 kilogram ball moving at what?
12 meters per second. Collided on with a 2 kg ball. Collided.
Okay, collided. Continue.
On with a 2 kg. Who is in the opposite direction?
So who is in the opposite direction?
2 kg.
So who has the 24 meters per second? Who has the 24 meters per second? Look at it. Okay, I've not finished writing it. Right, let me give you the question first, so you'll not be confused. Now, right, a 1 kilogram ball moving at 12 meters per second collides head on with a 2 kilogram ball moving in the opposite direction at 24 meters per second. Determine the motion of each other after impact. Determine the motion of each after impact. If there's a condition now, if E is equal to 2 over 3, if A, like if number A, you can use if I, E is not equals to 2 over 3, or you can use equal to 2 over 3, depending. So the point is, E equal to 2 over 3 simply means coefficient of restitution is there. All right, then you do for when the balls stick together and the motion is perfectly elastic. You do for all of them. Let's go. Can we read it now? The both of you, can you read it now?
Okay.
Oh, yeah.
A 1 kilogram ball moving at 12 meters per second collided on with a 2 kg ball.
Yes.
Which is in the opposite direction.
Okay.
At 24 meters per second.
At 24 meters
per second.
So that means if I write M1, our M1 is which ball? 1 kg. And that one was moving with a speed of 18, 12. The moment I want to come and write plus, am I going to write plus? No. Even if you want to write the plus, that means you do plus, open bracket. What size of that M2?
Minus
2. In velocity at 24, yes. Now there we go put the minus. The minus must follow am. Based on say the thought say move opposite direction. Do you understand what I'm saying? Then check now. Determine the motion of each after impact. Determine the motion of what? Each after what? Impact. After impact. So what do we do from there? Very good. So in this place here now, we know that M1 is what? 1. That's 1 times V, abi? Did they say they stuck together? They just said if they say given us condition. Or yeah, just this side here, what are we writing? M1 is 1 times V1, which is what? V1. Plus this one now, what's this one? 2 times V2, which is what? 2V2. Abi? They don't tell us that they move in opposite direction or anything. Just like that. This equation now, let's make it simple. 1 times 12 now, waiting. Minus waiting. Equal to waiting V1 plus 2V2. V1 plus 2V2 is equal to, what's the value? Minus 36. Equation 1. Most questions like this that come with coefficient of restriction is the coefficient of restriction you use and get equation 2. What is the meaning of coefficient of, what does coefficient of restriction mean? They ask you. You tell them it is the relative speed of recession over relative speed of what? Approach. You can use the word ratio. I guess what I'm saying now. How do we represent it? How do we represent it? How do we represent it? That's like saying V2 minus V1 all over U2, all over U1 minus U2. You see how we said it? So coefficient of restitution, E, just say recall. Recall that coefficient of restitution, E, is approach. I mean, it's recession over what? Approach. So we're having V2 minus V1, recession, all over U1 minus U2, their approach. Now, looking at this thing like this now, no use and work. Because this question said that the coefficient of restitution is equal to 2 over 3, have you seen it? So I'll come here and put 2 over 3 here. 2 over 3 equals to, waiting me our V2. You don't have V2 and V1?
Yes.
Okay. That means we will put them there, but we will not put any value for them. That means I'll just come up and write V2 minus V1. Then down there, U1. Our U1 is 12, Abby. You write the 12 there. Minus what about U2? Normally there's minus in the formula, Abby. So having minus 24. That's plus waiting 24. Now, what do we have? 2 all over 3 equals to what? V2 minus V1 all over 36. True or false? Cross multiply for me. What do we have? 3V2 minus 3V1 is equal to what? 72. Divide through by 3 for me. What do we have? V2 minus V1 is equal to what? 48, if I'm not mistaken. 24, I mean. Thank you, sharp boss. 24. 24. So good. Equation 2. How many of you have seen how restitution has helped us to want to solve the equation finish? Because the normal equation could only give us one equation. But with restitution now, we now have simultaneous. Let's move on. From here now, From here now, what are we going to be having? Tell me. I'll be having what now? V1 plus 2 V2 is equal to minus 36. So that our second equation now, you know, if it is V1 that started before V2, that's why it must be for the second one to do simultaneous now. So that means I will start with what? Minus V1 plus V2 equals to what? Oh yeah, V1 cancel V1. 2V2 plus V2 now waiting. 3V2 minus 36 plus 24 now waiting. Minus 12. So our V2 is equal to what? Minus 12 divided by 3, which is equal to what? Minus 4 meters per second. Is that all we're looking for? No. We are supposed to look for V1 also. What's going to be our V1? We can put anywhere. Equation 2, Abi? Equation 2 makes us understand that V2 minus V1 is equal to what? 24. What's the V2 now? Minus 4 minus V1 is equal to 24. Carry that one there, carry this one here. We're having minus 4 minus 24 is equal to what? V1. V1 is now equal to minus 28 meters per second. So you see, that's how we handle this. Eh? Yes, now. Yes, now. Question not finished. Nice one. Nice one. Those are the two most important aspects of dynamics. The two most important aspects of dynamics. Finishing. And dynamics finish, destroyed. Dynamics destroyed. Now, we are moving further. We are moving further. We're moving further. Now we're going to gravitational field. And under gravitational field, I will want us to solve questions from Kepler's law. Yes, questions from Kepler's law, the complete equation, utilizing Kepler's constant. Yes. On the lecture video already online, we have uploaded about the Lagrangian points and your regions of perturbation. You can go there and learn more. But for now, for the case of this class, we'll limit it to what we have for now. So good. Gravitational force. Gravitational force or field rather. Let's move. Okay. So we are going to gravitational field. And all right, very good. I've seen the question we need. All right. Okay. Now we are going to be having questions from gravitational field strengths, and others. The question says, right, the Earth has a mass of, the Earth has a mass of 5.9 times 10 raised to the power of 24. .97 times 10 raised to the power of 24 kilograms. and a radius of 6.37. Radius of 6.37. I'm talking about radius of the Earth. Times 10 raised to the power of 6 meters. Determine the gravitational field strength at the Earth's surface. Determine the gravitational field strength at the Earth's surface, given that G is equals to 6.67. All right, let's do it. The gravitational field strength of the Earth is given by what formula? I'm not just going to write the formula for you so that you just cram. No. It's simply what? Remember that force is in the same very, like the way force operates, is the same way weight operates, Abby. So we know weight is equals to what? Mass over what? Gravity. So if I want gravity to stay low, what will I do? Divide both sides by what? M. Because ordinary gravity is your specific field strength. That thing they are calling gravitational acceleration is the same thing as your gravitational field strength. Yes, it's the same. So how did I get it? By saying force divided by m, Abi. I will now come to my normal gravitational force formula. What is the gravitational force formula? Embarrass that formula. Gm1. Abi? Very well. I'll come to it and say divided by m. Because that's what this thing, how else I did there. Yes, sir. It's okay. All right. Like this. Okay. So, I will just 1m cancel 1m. It remains gm over r squared. It remains gm over what? R squared. Yes. So we'll come to this side. And say what? Small letter g that people used to call gravitational acceleration, which is also the same thing as gravitational field strength, will now be equal to what? Gm over r squared. And this is the formula we're going to use to solve. Do you know why we have to use it to solve? That's the safest formula to use. Why? Because it will give you information about any planet's gravitational acceleration. Any planet, to review their gravity, whether the moon, whether the Mars, anywhere, it will review their gravity. Once you know the mass of that planet, you know I'm looking at you because I see you traveling out of this planet. You see, once you have this value and this other value, I can write it for you somewhere. Forget, everywhere is good. I assure you. You won't stress. Where would you like to build your house there? Pick any space. Only you are the owner of the land. The major pioneer. So now that will be what? Equals to what? G is what? 6.67 times 10 to the power of what? 11. Times what's our m? The mass of the planet, Abi? 5.97 times 10 to the power of what? 24. Divided by what? 6 point what? All squared. Oh yeah. Let's solve. Follow my sister. No, then. You must get 9.81 for us to know that we are doing something. If not, we are just joking. From there around that range. Is it calculating the person? Can't you do it once? Your answer must be 9 point something. You know what you mean? 9 point what? You can see that is value. So that thing that we're calling as gravity, in fact, the real name is the gravitational field strength. Because that's what actually defines the weight of the body, which is like the strength of that body. So G is equal to what? 9.81. But if I want to write the units, I won't want to write it at least by second year because I used this method to approach it. I want to write what? Newton. What can I tell me? Like how? You don't know how to press calculator, you. There's no time to lose by anything. Already, Abi. Then by the time this one open. Minus 11, Abi. Sorry. The real constant. You understand what you're saying, Abi? Yes. So you don't cry. They know because real life. No minus. We know where we are solving to. So you know that kind of thing when we know where we are solving to, we're just solving for the solving sake. So that's it. Newton per what? Per kilogram. They should not let that to your ones. This is per meter. That's the answer. That's the answer. That's the answer. Now let's look at something. Let's look at something sharp. My OG. Greetings to you. Now look at you. I mean, I don't know passing now. You have heard it before. What's the formula for gravitational escape velocity and orbital velocity? Let me rush in the public now. When your brain click fast. It's the way your brain click. You know, it's this clicking. You used to click slow. So you hate shame. No, what would I have called you? Oh yeah. When I'm not calling you animal, not tell you, let me go and do something for them, give it to them one so they can see the move face. Oh yeah, let's go. Determine the escape velocity from the Earth. Physics have not added escape velocity from Nigeria yet. Now if they add it, we will hack the formula straight up. Determine the escape velocity from the Earth and find the orbital speed of a satellite 500 kilometers above ground. 500 velocity above the ground level. Orbital velocity. Orbital speed of a satellite around the Earth. Of the satellite 500 kilometers above the Earth. 500 kilometers above the Earth. How we go? Now, what do we do? What do we do? Okay, so I'm having this at my this. So gravitational orbital speed, and escape velocity. What is the orbital speed? What is the escape velocity? What's the formula for escape velocity? I didn't hear you. I don't want that one. No. That one is too direct. Do. It's a shameful life. Just to use this thing. So, what value? Escape velocity. Can we find the escape velocity?
Yes.
So what is it going to be? Let's go. Mass of the planet is what? Let me see the question now. It must be the escape velocity of the Earth. It's constant. Yes, because it doesn't change every time. Put it there. What's the value? 5.9. What's our R? Yes. That's the radius of that is something.
500 times 10
No, not that one. The normal radius of the Earth.
That is 6.37. 6.37 times 10 is 6.
Times 10 raised power what? 6. Times 10 raised power 6. Okay. So what does that give us now? Oh yeah, now, why is school like this? Do you need a calculator for it? How to do it to your brain? Oh yeah. Which one are you getting? Escape velocity. What's the value? You're not sure. That's the answer. Was it not 1.1 something or so? So like 5. Jesus. Come and see it. You know it's shameful thing you did to yourself. 1.1 times 10 raised power 4. Is it velocity back? Meters per second. How can you get the answer not to speak? I'm laughing. How about orbital speed? Orbital speed, what was it? Orbital speed, what was it? 6 linear movement required. Collect the mic talk. Oh yeah, start directing. Formula for orbital. What is the difference between escape velocity and orbital speed? Escape velocity is the minimum amount of velocity required for an object to just leave the Earth's gravitational field, Abi. But what about escape velocity? I'm sorry, orbital velocity. That's the velocity that helps to maintain satellite motion around their what? Planets. Maintain is one, the other one is just escape. So if you have the ability to escape, you don't have the ability to maintain. You will see loss. You get? So that's why you need to know those two formulas there. You need to know them well. So basically, the formula is GMR. There's no square there. GMR. I will get that here now. So start punching it for me in the calculator. Orbital velocity. Yeah. Orbital velocity. The square root now. GM over. Now, if you look at it, that orbital velocity that they mentioned that somebody was going to view it from up, Abi. So we have to put what there? R plus what? H. Where H is the height above the ground. Where H is the height above the what? Ground. Please, let's know what we are doing. So good. That gives us what? Velocity orbital to be equal to what, please? G is what? G is what? Multiplied by, what will be M? 5.97 times 10 raised power of what? 24. Divided by, what's our R? Radius of the Earth?
6.37 times 10 power 6.
6 point what?
37.
37 times 10 raised power of what?
6.
Is that all I'll do there?
Oh, plus
Plus what?
5 times 10 power 5.
Where is it right now?
That's 500 kilometers.
Is that what it is?
Yes.
So 500 kilometers is 5 raised to S.
That's 5 times 10 power 5.
Oh yeah, build for me. What will this give? Orbital velocity equals to what? Sharp? I can see 7.62. Okay. Now we are firing straight up to work, energy, and power. We'll be solving from some questions now under work, energy, and power. Under work, energy, and power. In less than powers, you don't break the person record. I don't think that you're more accurate. That's going to teach me. It's a good thing, I'm proud of you. Yeah, you're accurate. Shut up. Let's start. Oh yeah, work, energy, and power. You know that work is force times distance moved in a given direction. Have you seen it do? Have you seen it do? It's not like that. They wanted to pay for that. I just think that yeah, wait more. Let's seriously, God ready. They wanted to pay for that. So this question is coming from variable force and work by integration. Yes. Variable force and work by integration. Now, right. A particle moves along the x-axis under the action of a variable force. 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 And then we have the variable force F as a function of x. Please, if you don't know how to write F as a function of x, wait, let me write it. Why are you waiting for? I don't know math students. This is what I mean, no. F as a function of x. equals to 8x squared minus 6x. 8x squared minus 6x plus 10. Plus 10. Where x is in meters. Where x is in meters. The particle move from Bozellite, I greet you 100. The particle move from 1 meter, x equals to 1 meter to x equals to 5 meters. X equals to 1 meter to x equals to 5 meters through that action of a variable force. The question here now told us that we should determine the work done by the force and the average force over the interval. The work done by the force and the average force over the interval. It's very, very, very simple. It's not a complex something. It's not a, do you know how to go about it? Thank God, thank God for life. Thank God for knowledge. So happy. So happy for you. I was thinking you said don't know how to. God be for you. The Lord has done for you. Okay. So they said we should do that by the work done by the force. Determine the work done by the force and the average force over the interval. Work done by the force. Follow me. This is what we're going to be doing. Is that for me? Good. It's not for me. Okay, this is what we're going to be doing. Now, Fx is equals to, what do we do if we want to convert this force now to work? We integrate. Thank you very much. That means we just say, integrate this F in respect to what? X. That's like saying we are integrating 8x squared minus 6x plus 10. Abi? Very good. So what does that give us now? We'll be having 8x over 3. How do we integrate? Plus 1. Add up the 2 plus 1 under it. We have minus 6x squared over what? 2. Plus 10x, Abi? Plus c, arbitrary constant. Abi? Which is still remove. I know. Still remove. I'll leave it for solution's sake. Plus the fact that I know is teaching you. I'll leave it. So what do we have now? Year 1, year 3. 8x over 3 minus x squared plus 10x plus c plus 10x plus c. Sorry, oh. Cube, yeah. Thank you so much. Cube, thank you. That when the eyes of my organs them are on board. Some level of confidence, 100%. 10x, then cc. You understand what's going on? You understand now? So from here now, we have gotten the work something. It's just that we now know that we have to confine it to the limits, Abi. Because they told us that we needed it to be from 5 upper limit to 1, Abi. The distance from 1 to 5. So from there, we can just put it for 5. Put 5 here, ba. So we're doing for 5, we subtract for 1 from it. So that means we're doing 8 into bracket 5 raised to the power of 3 over 3 minus 3 into bracket 5 raised to the power of 2 plus 10 into bracket 5 plus, let's remove the c now. Because when we minus, they will remove. So this one is 1 to 5. Okay, you're pressing it straight, I know. That's what you like to do. So let's be doing for the other one. Blessing. Let's do space for this blessing. This is one answer. So this one I want to put 1 inside, Abi. 1 cube over 3 minus 3 1. Now, you can be doing this one for us. Madam, where did you branch? Since you not talk to, where did you branch?
First one. The first one is 90. Now transfer by 4.
What looks like 900 here? Okay. Over 3. Okay. So 900 and what? 900 and what? 25 over what?
And that one is 29 over 3.
25 per 3. What? Why not say over 3 here? Why did you do me per 3 here and do over 3 here? Are these different things? Or same per 3. What's the value now? It's not that called fractions. If this is good, you call fractions, you're asking me. My Lord will shock you. We are present. Everything else together.
896 over 3.
Eh?
896 over 3.
Divide this thing now. I mean, of course, you're already again.
298.67. 0.67.
So you're not cry. But what about that, those ones that said average force? I should calculate the average force. How can we calculate that? We're just going to do work over this thing now.
Is it average force or average force?
Average force. That is work done over changiness. I think the try thing. Okay. The second part of this same question. The second part of this same question where they said. The second part of this same lecture where they said that we should do what? Average force. Yeah? Average force. Average force. The answer now. Average force is this answer we got. Divided by. Yes. Yeah, that's the average. I'm just spreading that total force into each of them. So average force means oh Jesus, well. I've missed this crew. I mean, I was planning to come to today. So sorry. So what do we have? 298 F average will now be equal to what? Work done over what? By change in X, which is equals to what?
98.675. That is 5 minus 1. That is 74.6675. 6675.
All right. All right. So now we are going into circular and oscillatory motion. Circular and oscillatory motion. Circular and oscillatory motion. Circular and oscillatory motion. So, in this aspect, we are going to be looking at simple harmonic motion and some other things. So, let's write this question down so that we can deal with it. Let's go. A particle performs simple harmonic motion. A particle performs simple harmonic motion. A particle performs simple harmonic motion. A particle performs simple harmonic motion with amplitude equal to 0.15 meters. With amplitude equal to 0.15 meters and frequency equal to 3 hertz. And frequency equal to 3 hertz. Determine A, angular frequency. B, maximum speed. C, maximum acceleration. Now tell me somebody, what's the first thing they say we should look for there? I don't hear you.
Angular frequency.
To get the angular frequency, what's the formula? Angular frequency equals to what? 2 pi what? F. Are you sure that now?
Yes, sir.
2 pi F. Then what does that give us? 2 times 22/7 times what's the frequency? 3 hertz. So tell me, final answer please.
Answer is 18.857 rad per second.
Rad per second. Yes. What's the next thing they ask us to find? Maximum speed. How do you calculate your maximum speed? Maximum speed is equal to angular velocity multiplied by amplitude. True or false? So that's your maximum speed. Vmax is equal to angular velocity amplitude. Vmax V max is equal to what? Angular velocity multiplied by amplitude. So that the V max is equal to 18.857 times. What's the amplitude?
9.15.
I don't hear you.
9.15.
Yeah.
2.83.
2.83 meters per second. Did you just say right? I heard right. What did you say? Post. You're the entire of your house. The final one, maximum acceleration. Maximum acceleration. Maximum acceleration. (18.857) square times amplitude. Oh, yeah, now.
About
Everything together.
yes, 53.34.
How much again? Okay. 53. 3. Oh. I like this one now. A particle exhibits simple harmonic motion. A particle executes simple harmonic motion according to the expression. See the expression here. It said x is equal to 0.08 cos 5t. X is equal to 0.08. X is equal to 0.08 cos 5t. Okay? Tell me. Tell me from your notes, what's the first one? Okay. Determine the amplitude, the angular frequency, the frequency, the period, the minimum velocity, the maximum acceleration. The maximum acceleration. Okay. Okay. So let's get those things done one at a time. We know that the relationship is that x equals to a cos weighting angular velocity t. So therefore, weighting the arm. What's the first question there? Find the amplitude. A is equal to what? I know you. 0.08. That's the answer. Second one.
Angular frequency.
Uh-huh.
W is equals to 5.
W like this
Yes.
is equal to what?
5 right per second.
Yes. Uh-huh.
Find the period. That is
I don't get it.
the next one. I'm going to find the period.
Okay. T. So how do you get on? That is. How do you get on? From here we can get it.
T is equals to 5.
Yes.